So, like I said, welcome to day one of core training. Now, this is, like I mentioned in the email, even though we've been doing this for a year now, it still feels a little bit different from the way we normally run training. And so I'm going to try and replicate the in-person experience with the training class as much as I can. Unfortunately, there will be times when you just have to listen to me talk for a whole long time. But hopefully, once we get past some of the initial lecture, you'll find that there's a lot of time to do some hands-on work with the software itself and ask questions. And I really want you to feel comfortable to ask questions really anytime that you might have them. It works better if this is more of a dialogue than it is a lot of lecturing. It's more fun for me. It'll probably be more fun for you. So anytime that you have a question or you're not sure about something, just go ahead and let me know, and I'll be happy to try and expand and add more detail to the stuff that you guys are interested in knowing about. Because this is the core training class, that means that these are kind of the core principles that I've decided that are kind of the core ideas that everyone needs to be exposed to in FlexSim, regardless of your industry or background or any kind of influencing factors there might be on the projects that you're going to build after this class. So one of the first things that is kind of important to talk about is what we are talking about with regards to FlexSim and simulation. And so I like to spend a little bit of time just introducing the concept of simulation as it pertains to the FlexSim context, because simulation itself can mean a lot of different things to a lot of different people, depending again on your exposure, your background, things that you've done in the past. And so I just like to make sure we're all on the same page with what the definition of a simulation is. And the easiest way to define that is that we are trying to imitate some system of behavior that exists in real life. So the whole reason why we build a simulation is because we want to learn something from that simulation that we couldn't learn or would have a hard time learning without the aid of the simulation. And so we want to imitate that system by combining knowledge, facts about the system, about the way things work, and putting that together with simplifying assumptions in order to make it so that the model is usable and is easier to build in certain respects. That's one of the things that we're going to spend a lot of time talking about this week, is building your model to a level of detail that makes sense based on what you want to get out of the model. So just kind of setting up this idea, one of the things that you're going to find out is that a lot of these systems of behavior that are out there are so complex and there's so much detail to them that it becomes important to understand what level of detail actually matters to the model that you're building. Because there's going to be some details that matter a lot, and you'll need to pay more attention to that information, that level of detail. And there's going to be some things that don't matter as much based on the goals that you have for your model. And so you're going to want to think about how to assume things to be true to make your model easier to build, or even just leave certain parts of the system out because it doesn't have an impact on what it is you're looking to learn from the system. Now, the simulation environment of FlexSim is what we refer to as a discrete event simulation engine. Now, you can spend a lot of time talking about what it actually means to be a discrete event system like FlexSim and a lot of like the cool like behind the scenes things that are going on with discrete event. But really, there are two main things that I want you guys to kind of be aware of that will have an impact on the way you think about and go about designing simulation models. And that is this idea of events that take place in a system and states that change due to those events. So as the modeler, you're going to have control over the events of the system. The events of a simulation are essentially the things that you describe that define the behavior, the workings, all of the ins and outs basically of how the system behaves, where things happen, why they happen, with whom they happen, and pretty much anything that influences the execution of your events. Now, it's important to realize too then that a simulation really is just a collection of events. When you design a simulation model that imitates a system, you are designing the events in such a way in order to mimic the real life events that take place in that real system. Now, on the other side of that coin is this idea of states. The states that change in a simulation change in response to the events that you design into the system. So basically, when we're talking about state changes, we're talking about things that have changed in the model because of the events that are taking place. And this is how we gather output information or statistics about how the system actually is behaving. So an event takes place and that causes some kind of a state to change in the model that allows you to observe that state change and understand that this event causes these outcomes. And so the events become the way the model is configured, and the states become the ways that you measure the way the system is behaving. So one of the big things, again, to kind of take away from that is keeping in mind that everything that happens in a FlexSim model is driven by these events. And so if there's something that you want to cause to have happen in your model, it will be up to you to implement the event in the right way, in the right order, in order to allow the event system to mimic that real world system. And that leads us right to a short discussion about the difference between modeling inputs versus modeling outputs and being able to distinguish between the two of them. So when you're designing a model, you have control over what happens and why it happens and all of that. And these essentially make up what we describe as modeling inputs. Modeling inputs is information or data that you as the modeler need to be able to bring to the table to describe the way the model behaves. So different modeling inputs might be things like arrival rates, like how often material arrives into the system, a number of available limited resources like tools or machinery or people that need to be involved in the various events of your system, or the time that it takes to do things. And so you bring all of that information to the model, and you design and configure the model based on the inputs that you provide. And then the natural execution of the model will provide you outputs by changing the state of your model due to all of the events that you design into the model. So in order to produce outputs from your model, you need to build a model that produces those outputs. Because what we don't allow you to do with the way that we build models is you're not allowed to dictate a certain output target as something that you want your model to produce. You design your system, you provide inputs, and then you see what outputs are naturally resulting from the way the system is designed. So when you design models, you think about the inputs as they relate to the outputs that you want to achieve. Okay, so this relationship between inputs and outputs is important because it's the same thing that we just talked about events versus states. Because the events that you provide to the system is what directly leads you to the state changes of your system, which therefore leads you to the outputs of your system. So that means that it's really important to identify outputs of interest. So you'll need to do some thinking about, okay, if these are the outputs that I want to receive from my model, the results that I want to see, then what are the inputs that have a greater impact on the outputs that I'm interested in? So when you're thinking about a simulation model, again, kind of thinking about things in terms of, okay, these are the events that are going to happen. These are the outputs that I'm looking for. It's important to keep in mind that a simulation model, in addition to being an imitation of a real system, should be a purposeful abstraction of that real system. So there's kind of two ideas there that I think are really important. This idea, first of all, of being purposeful, I think is really important to a simulation model where you think about what the job of your simulation is going to be, identifying questions or problems that you're looking for your simulation to help you solve or answer. And so that's what I'm talking about here when we say that a model is purposeful. You want to build a model knowing kind of what you want it to teach you, because a simulation model is just a tool to help you learn something new. And so you should design your simulation models in such a way that you understand what it is exactly that you want it to teach you. One thing that's really, kind of an easy thing to fall into when you're designing a model, I've seen it happen in my own projects and other people's projects, that if you don't have a clear definition of what you want your simulation to teach you, it's really easy to fall into the trap of just trying to have your model solve all of the world's problems. That's really, really hard to do, because a model that is trying to essentially be all things to all people is hard to develop, it's hard to maintain, and it's hard to get information out of it. So what I often recommend to people when they're saying, well, how do I know how to go about starting a project and managing a simulation project, is I tell them, identify a few questions or problems that you really want your simulation to focus on, and build simple models that are really targeted and focused to learn or fix those particular things that you outline for it. Because if you just sit down at FlexSim and say, well, I'm just going to build a model of everything that happens everywhere, that's a really hard thing to manage. Now, because we want our simulations to be purposeful, that often leads us to leverage abstraction as a way to simplify parts of the model that aren't as important to the questions that we're trying to answer. If you have a good idea of what you want your model to teach you, then it's a lot easier to identify parts of the real world that have either low impact or no impact and can either be abstracted for simplicity or even left out of the system altogether that you're designing. Now, kind of going along with this and understanding, what matters, what's impactful, what's less impactful to your model, are these three categories of time management. Working with a simulation model really is about managing time. The time that you spend waiting for things to happen, the time that you spend actually doing things, and the time that it takes to get from one place to another. So these are basically those three categories, this idea of a queuing time versus a processing time versus a movement time. And so as each of these three categories of time have a greater impact on the way your model behaves, then you may need to spend more time understanding the rules about how things like queuing, processing, and movement actually happen. And if you can think about what categories your delays fall into in your simulation model, again, it helps you understand where most of your time is being spent, what kinds of time delays are very impactful versus less impactful, and also, therefore, what parts of your model need a lot of attention to detail and what parts of your model can be abstracted more simply in order to make it easier to design a model. Like, for example, you take something like the movement category of time. If your model is very dependent upon movement, then you need a lot of detail to describe it. So like if you have like an AGV network where you have vehicles that need to follow very specific routes that happen in very specific ways with very specific speeds, with very specific conditions, then you'll need to spend a lot of time managing how that time spent moving impacts the rest of your model. And you might need a lot of detail and a lot of rules about how that's handled. But in some models, movement is either very infrequent or the time spent moving is very short to the point where you could abstract it away as being a zero amount of time. Maybe you don't even bother modeling it at all because it doesn't happen very often. Or when it does happen, it's very short. And so those kinds of models that don't depend a lot on movement, they don't need to worry so much about the rules about how movement takes place. And so thinking about each of these categories critically like that can be a great way to help understand what matters in your model. Do you spend a lot of time thinking about the rules that are centered around queuing? Do you spend a lot of time thinking about how processing works? A lot of time spent about how movement works? Is that very impactful to your model? And hopefully that will, again, help you understand what inputs matter based on the inputs that you're trying to arrive at. Okay, so right along with that, again, we're kind of speaking philosophically about how to manage a simulation project. And one of the most scary things, I think, is a blank screen, right? When you sit down at FlexSim for the first time, you think, okay, I'm going to build a model. Where do I start? Before you even create your first object in FlexSim, I think it's a good idea to do a little bit of planning and ask yourself some important questions about the simulation that you're trying to build. And so these are some questions that I use in my own projects. And when I'm consulting with other customers, these are some questions that I ask to try and get to the root of what it is they want to learn from a simulation model. And this isn't meant to be like a totally comprehensive set of questions, just some examples of things to think about when it's time to plan your first project. And the first most important one we've kind of spent some time talking about, which is why are you building a model at all? What is the driving question that is leading you to design the simulation? What is the insight that you're trying to gain from your model? The second question, though, is a little bit interesting, where I'm talking about this idea of what is the central actor of a model. Now, the central actor, this is a term that I've kind of come up with, trying to do my best to describe this idea that there is some central force in your model that is driving all other behaviors. And different models are going to have different examples of what a central actor might be. But the idea behind it is that there, like I said, is some influence, be it orders that come into a warehouse or customers into a store, or work orders to assemble different parts in a system. There is some central driving force that says that if I didn't have this central actor, then nothing else in my model would actually do anything. So you imagine something like a hospital, for example. You might have like a really great simulation of a hospital with doctors and nurses and X-ray machines and MRI machines and all this other cool stuff. But if you think about it, all of it doesn't do anything unless there are patients, right? And so the central actor then is the patient, because that is the thing that drives all of the other functionality of your model. So And thinking about designing your model, you might have to think about what are the central actors in your model going to be? What do they represent? And you might also need to think about if they should be or can be categorized into various types, maybe because these different types of central actors, though they be like the same class of entity, they have different types that might influence their behavior and the way they flow through your system. You might also need to think about different kinds of arrival patterns. How did the central actors arrive? Do they arrive on schedule? Did they arrive randomly? How are they introduced into the system and thereby cause all the other entities in your system to react to their presence? And then think about how they behave, like where do they go and how long are they there for? And this may not necessarily be physically, but rather they may be just iterating through a set of steps, which may require different time delays related to processing, where they may require different limited resources to be available to them, and to think about how they progress through a logical flow of processing steps. Sometimes that means they actually need to physically go from one place to another, and sometimes they may not. So it just depends on how the system is defined. And also, like as I kind of alluded to, is also thinking about the limited resources that need to be available to your central actor as they want to progress through a system. Are there tools that need to be acquired? Are there people that need to work with the central actor? Are there machines? What sorts of bottlenecking factors might there be as the central actor flows through the set of steps that you define for them? Which leads directly to these 3 time delays that we just mentioned earlier, where you might need to think about queuing as a result of waiting for resources to become available, processing as you execute different logical events in the model, and movement as you move from place to place. And that goes right to this other question where we're saying, to what degree does the physical layout affect model behavior? So again, transportation rules that might need to be followed as it pertains to distances, routes, timing of those routes, and so on. Okay, any questions there at all so far?
No.
Okay, so just keep in mind that every model is a little bit different, but asking yourself kind of these kinds of critical questions are really important to helping you figure out what matters in the model that you're going to build and getting really to the heart of what it is you are looking for your model to teach you. So now that we've talked a little bit of philosophy about simulation in general, in this next section, we will get into FlexSim and seeing the tools that we have available to us to build a simulation model. And one of the first things that FlexSim wants to know from you about the way your model is configured is how to treat distance and time in your models. So this is an important idea where you need to think about how time is going to be measured and also how distance is going to be measured in your model, because these are things that will have an impact on the way your model is designed. It'll have an impact on the way your model reports outputs from your simulation. And so you want to choose a time unit that makes sense for the way that you think about time in real life. So if you're thinking about things like, well, we have these processes, processes X, Y, and Z, and we mostly think about them in terms of how many minutes they take to execute or how many hours they take to execute, then you want to choose a time unit that agrees with the way that you generally think about time in your model. And the same with distance. If distance is a very impactful input to your model, then you'll also want to think about how you define distance and how you generally think about distance problems in your model. So again, like if you have an AGV network, travelers in a model, or conveyor systems, then thinking about things in terms of the proper unit is an easy way to make sure that you're thinking about things the right way. Now, one thing about these units that we make you choose at the beginning of a model is once you choose them, you're not allowed to change them. This is a design choice that we made to basically say that once you choose your units, that's what they're going to be. You can't change them, because then we would have to have like code running in the background that constantly says, oh, if you change your units, then the way you define things like time and distance, we have to guess how to automatically update them into your new units. And that's actually a hard problem for us to solve. So instead, what we did is we put the onus on the users to say, when you start a model, choose how you think about time and choose how you think about distance. Now, the defaults that show up on this window can be changed so that instead of defaulting to our defaults of seconds and meters, You can have it default to a set of units that is more typical for the models that you build, and that's fine. But just once you say okay to this window, the way that time is measured and the way that distance is measured gets locked in to the model. Okay, so let's actually take a look at what that looks like. So if we come over to a FlexSim model, where I have FlexSim launched, but I haven't actually started building a model yet. And if I say new model, that's when the model unit window pops up and it wants me to choose how I measure time and how I measure distance. Now, the fluid units, you're probably not going to have to worry about too much. You only have to worry about this if you're building models that deal with like material flows in terms of like volume, as opposed to discrete entities. And not very many people build models that way, honestly, but it is a unit that you would have to consider if your model depends on volumes. Below that, though, there's also a model start time. And this model start time is something that you as the user can change at any time that you want, where you can decide what the zero time of your model is going to be. So this means that the model start time defaults to 8 a.m. on today. Whatever day it is when you launched FlexSim, that's what it treats as the model start time. But you can change it here using this calendar-based interface, or you can change it in the global preferences of your model at any time. But once you say okay to that, we lock in our time and our distance, and it draws in the 3D grid and the main interface of FlexSim. I want you to note up here, there is the run clock that says that it's 8 a.m. today, which is our start time. And then in the brackets, it says that that is time zero. So time zero is what we refer to as the beginning of your model. So the zero time of your model would mean that this is 0.00 seconds, because the model unit that I chose for right now is seconds. And the model clock will change based on ticking through subsequent seconds when the model begins to run. Okay, now the time unit that we chose influences the model clock up here where we see runtime. And then our distance unit has an impact on the grid. So in the grid, we have a Cartesian coordinate system that is based on a number of grid spaces that is equal to one of your distance units. So like, for example, if I just zoom in a little bit with my scroll wheel, I can see that I have a square that represents one distance unit. So it is one distance unit by one distance unit. So this would be a 1 by 1 meter square. If you zoom in a little bit further, you can see that 1 meter square actually get divided into subsquares, where now we are down at the decimeter level. And if you zoom out, you're back at the 1 square is 1 meter. If I go beyond that, then I get little squares inside of my big square, where each of these little squares is a decimeter, or 1/10 of my distance unit. Okay, so each grid space that we move in the model represents moving 1 meter, because that's the unit that I chose. And so if you were to choose a different unit, then your squares would be a different size, and they would represent a different unit of measurement based on the unit that you chose on that screen. Now, in navigating this grid environment, if you hold down the left mouse button and move your mouse, that will pan the camera around in the view. You also saw with the scroll wheel, like I mentioned earlier, that you can use the scroll wheel to zoom in and out on the grid environment, so you can like change the zoom level of the camera. And if you hold down the right mouse button and move your mouse, you can pivot the camera around one point in space. So you can see that we have this three-dimensional environment where now we can create the world of our model. Any questions so far?
What is the impact of the that start time of your model? Like, why would you need to specify that, or what do you do with that?
Like in terms of the calendar time?
Yeah, or like just having that start time. Like,
yeah,
what would I fill in there and why?
Yeah, so the start time of your model is there because you need some point for the model to actually begin running, right? So like the first event of your model is going to say that generally something is created, that represents that central actor that we talked about, and then time will begin to flow from that point. We give you the option of defining the start time as a calendar date time, because some models run data from like a historical point of view, where you might have a gathered set of data that represents like what happened in January of 2020. And so you have all this data that is a result of like the real world system that comes into FlexSim. And you want to be able to run the model from the perspective that it's actually running that historical set of data through the proper time that it happened in real life to see if your model validates, if your model data validates what happened on that actual day. So we give you the date and time option so that you can have a better like relationship to the time as it passes in your model. There are some people whose models run for a couple of years of time. And instead of saying, well, this is what happens at the model at, time 3,700,602, you can say this is what is happening on, August 25th, 2022. So instead of measuring the time purely as a number of elapsed time units, you could also view it as the calendar date time, if that makes your model easier to understand.
I see. Thanks.
Yep. So the calendar really only comes into play if you're running either historical data or you're running like for long periods of time. A lot of times, though, what you really end up being concerned with is just how much time has gone by in the model. And so we have to start somewhere. So we start at time 0, and then we start counting time forward from there.
A quick question. Can we change this time later after we, let's say, build the model?
The start time? Yeah. Yeah. If you go to I think it's under edit, where you go to model settings, you can change, well, actually, no, it's not model settings. Oh, you know what? It's because, in 2021, I forgot, we changed where that stuff was located. It's now located directly on the run clock. So in version 21 of the software, I'm just getting used to the new interface too, where it says start time, it says that the display mode of the clock is both the number of seconds and the date and the time. And then you can set your start time here so that you can change the start time at any time that you want.
Awesome. Thanks.
So you mentioned that you can't change the default units. Even if I copy and pasted or copy this simulation and wanted to do a different unit, you're not able to do. You have to like start it from the very, very beginning, right?
Yeah. If you had something that was defined in another model that was using like a different unit and you brought it over into this model, then any time definitions would be treated as though they are the native unit to this environment.
Okay.
Right. And so it would be up to you to say, oh, well, I copied this from a model that maybe used hours as the time unit. And so this time definition that says something's going to take 5 hours, I now need to convert that to however many seconds it takes to get to 5 hours. You know what I mean?
Mm-hmm.
But you would have to do that conversion yourself, because we would just interpret the time value as being whatever unit the model is set to be.
Thank you.
Yep. Okay. So the grid then is the world where we design our simulation models, and the tools that we have available to us to build models are found in what we call a library. So on the left-hand side of your model, you will find the library panel. So in the library, we have right now a library of what we call objects that can be dragged and dropped into the grid. So each of these objects defines a set of behaviors, and we break these objects up into different classes. So the first class of objects that we're going to look at are what we refer to as the fixed resource objects. A fixed resource object typically is used to represent a location in the real world. And so these objects have different behaviors that they know how to execute. They have like a predefined set of events that they know how to do in order to produce behaviors that mimic the real world. Because they are typically used to represent locations where things happen in a model, we refer to them as fixed because they're not designed to be travelers in a model. They don't know how to move around in the model. And that's in contrast to the other important class of object that we're going to look at today called the task executor objects, which are mobile resources that are assigned tasks like being able to travel places and do things. Now, The fixed resource objects also have a really important function where their job is to send and receive what we call a flow item. A flow item is a special kind of object that is used to represent the central actor in your model. So a flow item could represent any number of things that you want it to represent. It could represent parts on an assembly line. It could represent orders that need to be processed by a warehouse. But a flow item's job typically is to represent something that exists in real life and is used to represent like a physical component in a physical process. And so flow items generally have fairly abstract shapes, but they can be modified to look like anything that you want. That helps with the comprehension. But generally, we just let them have these abstract shapes in order to represent things that flow through a system. So the job of a flow item is to represent a physical component that goes from object to object. And it's the object's job to define the system behavior. So objects execute events when they receive flow items. When flow items are present, they execute their system of events. When flow items are not present, then they just sit idle, waiting for the next flow item to arrive. And we define relationships between objects through the use of what we call port connections in order to define the interconnectivity of one machine with another or one object with another that defines how they relate to each other and how they can work with each other's event systems on behalf of flow items. So this is a lot of kind of like high level description. So let's actually kind of see this stuff in action. So I'm going to come back over to FlexSim, and out of my object library, I'm going to create some basic objects. And the first object I'm going to start with is what's called the source. The source object is very typically the first object that you create in a model because it is the source's job to create flow items. And flow items get created according to some kind of an arrival pattern where they're told to arrive maybe based on an interval of time or based on some kind of a schedule. And so the source's job is to produce flow items for other objects. Another common object is the queuing object, whose job it is to facilitate queuing. So flow items will come to a queue and they will dwell in the queue until some other resource that the queue wants to send the flow item to becomes available. Typically that involves a process. And so a processor object is often used as a way to cause a flow item to be delayed in accordance with some sort of a process or a procedure that needs to be done on the flow item. So like, for example, sending like a part to be machined at like a press or a lathe or something like that, where you have a process that says something comes here and it has to be here for this long in order to represent the procedure of whatever this process represents. And then the last object that we're going to show as an example here is the sync object. The sync object can be thought of sort of as the companion to the source, where it's the source's job to create things, but it's the sync's job to destroy things. And a sync, therefore, often represents the termination point of the model, where a flow item goes to a sync when we no longer care what happens to it beyond that point. So if your source often represents the starting point of your model, the starting point of your flow item flow, then your sync often represents the termination point of that flow item flow.
What's an example of a sync?
So it's an abstract way of saying this is the end of the process. So like maybe if this model that I'm building represents like a warehouse and I'm picking parts to be part of an order, and then once all my parts are picked, they get shipped. And so that might represent the sync. The act of shipping things might be the sync, because at that point, it's no longer part of the process that I'm modeling. That's the end point where I don't care what happens anymore to the flow items that I was working with. They reach the sync, and that's the end of their flow that I care about. You know what I mean?
Yeah.
So in abstract terms, you can think of the source as the beginning point of your model when flow items are first introduced to the system, and the sync as the termination point of your model where you don't care what happens to them beyond that point. You don't want the flow items to just linger on in the model, not doing anything. So it is good practice to send them to a sync to represent that we don't have any additional events that those flow items need to be involved in. So let's take a look at this model that we've started building. And to give a little bit of an understanding of how the FlexSim system works, I'm going to go up to the debug menu. And there is a window that I want to open from here called the event list. And essentially what the event list does is it shows me what events are scheduled to happen in my model. So again, this kind of goes right back to what we talked about before about the discrete event nature of the system of FlexSim itself, where we want to know what events are going to happen in our model. And the event list shows me what events are scheduled to happen. So right now, my event list is empty because as of right now, after having just put these objects into the model, there are no events scheduled to happen. But if I come up to my toolbar and find the reset button, and we'll give that a click, I see now that there is an event in my event list. And the event says that it's going to happen at time 36.19. The object that is going to execute the event is the object called source1. So that's my source. And the event type says that it is going to create a part. So this is the event that is going to create my first flow item. And also note that this timestamp on the event happens in the future. So again, notice the run clock, we're at time 0, the very beginning of our model. And we see here that we're going to execute an event at time 36.19. Now, if I hit run, my model clock begins to advance. And then when I get to the time in the event list, the event comes out of the event list and my model clock stops because my event list is empty again. Okay, so an empty event list means that your model isn't running. So this is kind of like one of the first things to look for, like debugging wise in a model. If your model just seems to stop for no apparent reason, check your event list to make sure that there are still events scheduled to happen. Because we've hit a point here where we executed an event at time 36.19, and the model clock now shows that at time 36.2, my model has stopped because we've run out of events to execute. And if we hit reset again, that brings me back to time 0 on my model. And I can see that that timestamp with that first event is now back in the event list. If we hit run again, the model clock advances to the time of that event. And then when that event happens, it leaves the event list. And if there were other subsequent events to do, then the model clock would keep running and we would have an opportunity to do other things in the model. But as it is right now, the model just stopped. Okay, so let's think about why the model did stop. Well, like I said, it stopped because we ran out of events to do. And if we hit reset, we have another event that is going to happen. But where did this time come from? Why is the event happening at time 36.19? Well, because this is something that's happening on the source object, I can look at the source object's properties to understand how it is executing this event. So that's a key feature of all objects. Objects all have what we call properties that allow you to change input options on that object in order to affect the way it executes its events. And so if you click on an object like the source, the panel on the right-hand side becomes a way to influence the properties of that object. And we'll be able to take a look at what a lot of these do. But for right now, the most important property that we're going to look at is found under the source section, where it says we have the inter-arrival time. And the inter-arrival time is, if you have your mouse over it, it pops up a little bit of hint text that says, define the frequency of creating flow items in seconds. And so this expression is defining a value, a random number, that tells us how many seconds will go by in the model between the creation of each flow item. So it says that it's going to use what's called the exponential distribution. We'll talk more about that a little bit later on in depth. It's going to use the exponential distribution that says, on average, the time between creation of these flow items is going to be about 10 seconds.
Seconds because that's the default value for the time periods?
Right. It's seconds because that's the unit of the model.
So if we had a different unit of the model, then we would use a different, right?
Yeah, then this would be like if we chosen minutes, for example, as the unit for this model, then this 10 would represent 10 minutes instead of 10 seconds.
I just was noting that so the pop-up is gonna accurately tell you whatever your unit of measure is.
Correct. Yeah. Where it says in seconds, it knows that the model unit is seconds, and so it's reminding you here that, hey, remember this is seconds. But if it was hours, right, it would say in hours.
Perfect. Cool.
Yeah, there's a few places where we'll try to remind you what your units are. Like in these kind of like pop-up hint windows, we'll do that. And also in the model clock where it says display mode in seconds or date time or both. It knows to put seconds here because it knows that seconds is the unit of this model, but it would say minutes or hours if you chose something else.
Thank you.
Okay, now because the source is using this exponential distribution, that means it's going to be a random number. And that's why the timestamp on this event is a seemingly random number, because it just sampled a value from the distribution and said, we're going to execute that event at this time. But if you were to come to this input field, you could highlight all this text. If I type just a number like 25, then that would mean that the inter-arrival time now is exactly every 25 seconds. So if I hit reset now on my model, notice that my event list says, okay, now the timestamp for this event is at time 25, because we said that the inter-arrival time now, the time to create a flow item, is exactly 25 seconds. And again, that just means if I hit run now, my model clock will run up to the time of that event, which is now 25. And now the model stops because, again, we've run out of events to do. So how do we allow the source to continue creating a flow item exactly every 25 seconds like we have here instead of stopping? Well, this is where relationships that we create between objects becomes important. And we create relationships between objects using a mechanism that we call port connections. And a port connection is basically a way to allow one object to have some kind of a relationship with another. And the first relationship that we're going to look at is to define an output to input relationship, meaning that the flow item that is in one object can be output to another object and received by that object. So to define a port connection like that, we're going to go up to the toolbar. And in the toolbar, you'll see that there is a set of buttons next to our new open and save that are related to different cursor modes. And so here we have the standard cursor mode, which is what we're in right now. But right next to it, we have the option to connect objects. And if we click on the drop-down triangle for this, we'll see that we have 3 different options for putting our cursor into a connection mode. The first one we're going to look at is this A style or A mode connection that says to connect objects. So we're going to choose that mode. And when I bring my cursor back into the grid, you'll notice that the cursor icon is changed into a chain link. And this chain link means that we are now in a connection mode where we can make a relationship between 2 objects. We create that relationship by first clicking on one object like the source, and that gives us a yellow line that we can drag to another object like the queue. And so if I click on that object, that forms a link between them. And now notice that I'm still in a connection mode here. And if I want to get out of this, I can just right click once and right click again to get me back to the standard cursor. Okay, so I just want you to pay attention to this link between them, where we have a port terminal on the source and a receiving port terminal on the queue. So this now establishes an output to input relationship between these 2 objects. So now if I hit reset and run, again, at time 25, our first event is going to take place. And that event is going to create a flow item. And because now there is somewhere to send that flow item, the source will continue to make flow items every 25 seconds in the model. So now at time 75, create another flow item, time 100, create another flow item. And the queue is happy to receive these flow items because that's part of the queue's job. One of the things that the queue knows how to do is to receive flow items and store them if there's nowhere else to send them. So since the queue doesn't have an output relationship with any other objects, it's perfectly happy to receive the flow items from its input relationship with the source, but it doesn't send them anywhere because we haven't dictated any possible destinations to go to after the queue. Everyone see that okay? Any questions so far? Okay. So since the queue is now receiving these flow items, how many flow items is the queue willing to receive? Well, if we increase the run speed of this model, where I'm just speeding up the execution of the events, eventually we're going to get to a point where the queue is going to say that it's full. And if we click on the queue right now, we can see how many flow items there are inside of it right now. It says that its current content is over 600. We're approaching 700 now. And then when we get to 900, and then when we get to 1,000, the model clock stops again. And notice again that we've run out of events in the event list, because we've hit a point where the queue is no longer able to receive flow items. Because if we take a look at the properties of the queue now over here on the right-hand side, you can see that there is an input property that says the maximum content of this queue is 1,000 pieces. The queue can only hold up to 1,000 flow items at once before it considers itself full. And because it's now full, it's not allowing the source to send another flow item to the queue because it's saying, I'm not available. And this is part of the important behavior given to us by these port connections, where the port connection between the source and the queue is used so that these objects can communicate with each other to decide whether or not you can send a flow item to that object. So the source right now has a flow item. It wants to send it to the queue, but because the queue is full, the port connection on the queue is saying that that port connection is closed. So notice that the input terminal on the queue is red to represent that idea that the input terminal is closed. The queue can no longer receive any additional flow items. If we hit reset, that input terminal turns green to represent the availability of that port. So this object is saying, I'm available because my current content is below my maximum content, so you can go ahead and send me flow items. And so every time the queue receives a flow item, the port terminal stays green until such a point that the queue is full. So again, if we just sort of speed this up a little bit, get to the point where we have 1,000 flow items, again, you can see the terminal went from green to red to indicate that the queue is no longer accepting flow items. So the port connections have logic behind the scenes that you don't need to worry about, where the objects will communicate with each other and decide whether or not an available connection can be used. In this case, when the queue is full, it denies the entry of any additional flow items. Okay, so let's give the queue somewhere to send these flow items. Let's make a relationship between the queue and the processor. So again, I'm going to go back to my connection mode. I'm going to choose the A-style connection. And I'm going to make a connection from the queue to the processor, and also make one from the processor to the sink. And then just right click to get back to my standard cursor. Okay, so now if I hit reset, notice that the input terminals on the sink and the processor turn green. That's actually a really important thing. If you make any changes to the model at all, if you change properties of individual objects, if you make port connections, always remember to hit reset before you hit run. Because when you hit reset, that's when we figure out how to create these events and make sure that these relationships are all properly accounted for between the objects. So that's why every time I've made a change to the model so far, I hit reset. So just get in the habit when you're working with a model to always hit reset and then run first. So if I hit run, now I'm waiting for the creation of those flow items, and I can see that the event list has other additional events in it. It's like, for example, right now, if I stop the model, I can see that I have an event on the processor that is scheduled to end at time 185. That's the process finish. So we're waiting for the flow item to be processed by the processor. So there's an amount of time that a flow item will spend in the processor. And if we click on the processor, we can see what that duration of time is by looking under the processor properties and seeing a time assigned to a setup and a time assigned to a process. So right now there is a 0 amount of time set for setup. So let me just change this and say that we're going to have a 5-second setup and a 10-second process. And I'm going to reset and run it again. And I just want you to notice that when a flow item comes to the processor now, it stays in the processor for the duration of a setup time and then the duration of a processing time. If we look at the event list, we can see that there's the end of setup event, and then there's the process finish event, and then the flow item leaves and is destroyed by the sim.
Regan, is there any significance to the output for the source and the queue always being read over?
Yeah. So output ports are always read unless there is a flow item that is trying to use it. So it's actually kind of hard. It's kind of hard to see with the way this model is currently set up, because we never have like a blocking condition where an object is saying, hey, I want to send a flow item, but the place I want to send it to is busy, so I can't send it. But under those conditions, you would see that output ports turn green if there's a flow item that says, hey, I want to use that port connection. Because right now, when a flow item enters the queue and leaves the queue, it happens so fast that we never see the port connection change from red to green to red again. But that's really what's happening if you could actually like step through each of those individual events.
Got it. Thank you.
Mhm. Now, I wanted to draw your attention also the processor. If we are clicked on the processor and look on the properties panel, you also notice a section devoted to statistics. And this statistics window is something that every object has. Every object reports these basic stats about itself. It keeps track of its state, its throughput, its content history, and its stay time. So notice that the state data for the processor is changing. It goes from idle to setup to processing, and then back to idle again. Again, kind of giving us that idea of state change that we talked about before, that these events that are happening on the processor are causing state changes, where if the processor isn't doing something, it's in an idle state. When it receives a flow item, it goes into the setup state for the duration of the setup time that we define. And then it goes into a processing state for the duration of the process time that we define. And the total time spent in the processor, the state time stat, is showing me the combination of our setup time plus our processing time. So we can see from our state time data that flow items spend 15 seconds in the processor, which is our 5-second setup plus our 10-second process. Now that also means that because our source says that we're creating a new flow item every 25 seconds and our processing time is 15 seconds total, that's why you don't have anything in the queue, right? Because we're creating something every 25 seconds and we're processing it every 15 seconds. So there's never a time where we get build up in the queue. Right, but if we were to say that we had a like a 21-second processing time. So again, we have our 5-second delay for setup, and now we have a 21-second delay for processing, which means that we might see a flow item actually come into the queue and wait for the processor to become available, because the processor assumes that it can only work on one flow item at a time. And so that means that you get a flow item in the queue waiting for its turn to go to the processor. And so the processor has its input closed right now until the flow item that it has leaves, then it opens its input and then allows the flow item in the queue to be sent to the processor. And you can see that input terminal turning green as there is a flow item that wants to use that output port, but can't, until the port is reopened, and then the flow item can leave and go to the processor. Any questions so far? Is that making sense? Okay. So I want to show you guys one other thing related to the fixed resource objects, and that's if I had a second processor. So let's say that I've got a second processor, and I'm just going to connect those in. Oh, and I just realized I used the keyboard shortcut there because that's my habit to connect these objects. So I didn't go up and choose the connection mode. Instead, what I did is I held down the A key. And as you hold down the A key, that puts you into the connection mode on your cursor. And you could use the keyboard shortcut to make the connections if you wanted to, instead of actually going up and choosing the mode. It's really sort of a workflow thing, whichever method is most comfortable for you. But like I said, I'm partial to the keyboard shortcuts just because it saves me a click of having to come up here and choose a mode. I can just hold down the key and put myself into that connection mode. Okay, so I just wanted to use this as an example to see what happens if you have more than one port connection on an object. So notice now that the queue has two output ports, one port that goes to the processor and another port that goes to our new processor. So one connection to processor one, one connection to processor two. Now, if we hit reset and run now, how is the queue going to send flow items to these processors? So the flow item is going to come into the queue, and then the queue wants to send the flow item out to someone. And so that first flow item went to processor one, and that second flow item went to processor two. Another flow item comes into processor one. Second, or rather, our fourth flow item went to processor two. So what's the pattern here? How is the queue deciding whether to use the port connection for processor one or the connection for processor two? What do you guys think?
It's just using whatever was available in the queue, right? Just pulling the next one.
Yeah, that's the default mechanism that all fixed resource objects use. Is if there is one port connection, then it says I'm going to send to the first available port. If there's two connections, then we're still going to send to the first available port. And that's a property that we can observe about the object by clicking on it and going to a section of properties that have to do with the output of this object. So under the output section of the object, it says that there is an event called send to port. And send to port allows us to establish a logical rule that says how port connections 1 through n of however many port connections you might have can be used. So as you can see here, the send to port rule that's currently being used says just use the first available port. But if you go to the drop-down menu on this, you can see that there are other options that you can choose from. These are some pre-programmed options that we've built into the object that you can use. And we've also provided ways for you to establish custom logic that allows you to define what is the pattern of use for these output port connections. Like, let's just choose a simple one and see how it changes the behavior of the model. If we were to go to the option that says random, under the random section, I can choose a percentage to assign to each of my port connections, which means that there will be a random % chance that will cause us to use one of our port connections. So if I say by percentage here, it says that there is a % and a port that I want to use. So here I'm going to say that there is a 65% chance to use port number 1. And then I'm going to click on the green plus sign to say that there is a 35% chance to use port number 2. So because this option doesn't know how many port connections you might have, it wants you to explicitly assign a percentage to each of the port connections that you want to assign a percentage to. So because I only have 2 port connections, I only need to have 2 percentages and 2 port combinations here to account for my ports. But if you had like 3 connections, 4 connections, 5 connections, Again, it would be up to you to define the percentage chance associated with each port number. Okay, so let's see what this looks like then if I say 65% goes to port number 1, 35% goes to port number 2. So if I hit reset again, because I made a change to the model, I should hit reset. And now when I run, my first flow item again will arrive at time 25. And I don't know where it's going to go because it's going to be randomly assigned. Chances are it's going to go to processor 1 like it just did because that's associated with 65% chance. And my second flow item happened to get chosen to go to port number 2. So now my third flow item also got sent to port number 1. We'll just speed this up a little bit and get some more flow items. So there was a flow item that got sent to port number 2, 2 in a row. We didn't even go to port number 1, and that's fine. And like right here, if I stop the model, you can see that there is a flow item in the queue because it wants to use port number 1. Notice how port number 1's terminal turned green because this flow item wants to use that port terminal, but it can't because that processor is currently in use. Because that random chance is just saying that 65% of the time a flow item will choose to go to port number 1 as opposed to port number 2. So we could expect to see a bit of a queue develop for things that want to go to port number 1, while things that want to go to port number 2 maybe don't have to wait as long in the queue because that's associated with a less percent chance of choosing port number 2. But it is just random, right? Because we said that the port will be chosen based on a random chance of a percentage that you get to decide as the modeler. Question so far?
Will it throw some kind of error if you don't specify enough ports? Like if you just had %65 port 1 and then you forgot to do the second one?
Yeah, that's a good question. It won't give you an error. It'll just behave strangely. FlexSim generally tries to avoid like putting up an error for every little thing, because sometimes people may do things in such a way that you might think should cause an error, but it's actually a fine way to do things. And so we generally kind of take a step back and err on the side of not giving a lot of errors. So like if I were to get rid of this percentage chance, right? If I go to the queue and say we've only got the 65% chance to go to port number 1, right? Even though the model is running, it's running just fine. And basically what this means is that there's a 65% chance that you will go to port number 1, and the rest of the time you'll just choose whatever the first available port is. Because port number 2 will still be used, but only if it was not in that 65% chance that explicitly sent it to port number 1. So if I had like a second port and a third port, you could choose whatever was available out of port number 2 or port number 3, because it would just treat that as 65% chance to use port 1 for sure, and then a 35% chance to use any available port beyond that.
Yeah, okay.
Can you limit the source to quantity that it could possibly produce? Or is that just done by time and frequency? Yeah, that's a good question. So the source has a couple of different modes for creating flow items. The default mode that we end up using the most of the time in training is this inter-arrival time that just defines, an amount of time in the model between the creation of one flow item and the next flow item. But under the arrival style property, you can choose things like schedule and sequence, where you could use a more like, hey, you're only going to create this many flow items and then you're done, right? Like if you switch over to a schedule mode, you could define a timestamp when a certain quantity of flow items is created. And then once the arrival schedule is finished, then the source won't create any more flow items. So
the inter-arrival time assumes that flow items can just be created infinitely every interval of time that you define. But the schedule and the sequence might give you some additional options that you might want to explore for those kinds of situations.
Got it. Thanks.
Yep.
I had a question.
Yes.
So when we do reset of the model, let's say we don't change any parameter, does it also do a reset of the seed for randomization?
Excellent question. So if you have the option turned on for that, then yes. See, like right now, if you go to the statistics menu, there is an option that is on by default called repeat random streams, which means every time you hit reset, the random stream is always kept the same. So you'll always get the same random numbers every time your model runs. And we have that on by default because it's easier to debug a model that behaves exactly the same way every single time. And that's basically what this ensures, that the model will behave exactly the same way every single time. If you turn that option off, every time you hit reset, any random number seeds in your model will be resampled and will give you different random numbers every time you hit reset the model. So you get different results every time.
Got it. Thanks.
And right now, with the way this model is set up, all of the inputs are static anyway. Like my inter-arrival time is exactly 25 seconds. My processing and setup time are also exactly 20, so many seconds. But as we'll see later on when we talk about using distribution as part of like object properties, we'll see how that can change.
I understand. Thanks.
Could a single process have two cycle times? So let's say like I want to use a process to represent an equipment. So like the first input has like a cycle time of 25 seconds, and then the second time it goes through, it has 10 seconds.
Sure. Yeah, the processing time is a property that accepts expressions, which means that you could say that like right here, it's going to be a static 21 seconds every single time, right? But you could like set something up on it that says this kind of thing has this cycle time and this other kind of thing has this different cycle time. And so the processing time could choose based on what kind of thing it receives, or you could choose a different cycle time based on like what member of a sequence is going through. Like maybe you process 5 things as like a sequence, and the first one always has cycle time A and the second one always has cycle time B. You could program something like that into the cycle time as well to be aware of like sequence members and choose cycle times based on that. Yeah, it's a very flexible field. It allows for a lot of potential inputs. We're using it in its most simple version for now, but we'll explore some different ways to implement that. Like as we
Thank you.
Yeah. Okay, so I want to show you guys one last thing, and then we'll take a short break. And I just want you to notice that with the way this model is currently set up, if I move the queue a little bit, remember the Cartesian coordinate system where we are now a few meters away, right? We've got basically 6 meters of distance between the queue and the processors. But when the flow items leave the queue, they leave the queue and immediately arrive in the processor. There is no delay time based on travel with the way the fixed resources are operating. That is a feature of the way the system is designed. We assume that if we are passing a flow item from one fixed resource object like the queue to another fixed resource object like the processor, that the time it takes for the flow item to transit that distance is 0 time. So if you want to account for travel time in a model, we need to use a different kind of object that knows how to travel. And so in the library, there's a set of objects called task executors. Remember, we defined them as mobile resources that have the ability to travel around in a model. And so we often use these task executor objects to represent transportation resources like cranes or robots, forklift trucks, or people in order to have them be involved in the events of the model in order to execute travel delays based on the distance that needs to be traveled and the speed of the traveler. So for example, if we were to use something like just like the operator, which is used just as a task executor that represents a person, then we could choose, first of all, a different visual if we want to for the task executor. And then we bring her out to the model. And if I want to use this operator now as my as a transporter to actually be able to pick up a flow item from the queue and carry it to the destination processor, then I need to establish this operator as a transporter from the queue. And to do that, we have a couple of things we need to do. First of all, on the queue properties, under the output section, right below send to port, you'll notice there's a checkbox that says use transport. And this is unchecked by default for all fixed resources, which means that the queue assumes that it can just send flow items to whatever destination it wants without having to wait for a transporter to facilitate that movement. But if I check that box, now I'm saying, okay, queue, you need to ask for a transporter to come and take the flow item for you. And this activates a couple of other properties. We'll talk more about these a little bit later on. But for right now, the most important one is where it says that the transporter is defined using this expression. And this expression is basically looking for a port connection of the queue that knows how to find this operator. And so the port connection that we're going to use isn't the port connection that we've been using so far. In fact, if I were to use my A connection and try to connect from the queue to the operator, it actually won't let me do that. It's going to say that that's not a valid connection. It's just not going to let me, right? I make the connection and it says, nope, you can't do that because you can't make an A style connection or an output to input connection from a queue to an operator. So instead, what we'll do is we'll use our second kind of connection, which is called the center port connection, which allows us to establish a referential relationship between an object like the queue and an object like the operator. Notice that that port connection is drawn a little bit differently. It's drawn as a square terminal on both of the objects, and it's drawn on the center line of the object because it's called a center connection. It means it connects from the center of one object to the center of another object. And this relationship now allows the queue to say that I'm going to look at my center port connection and find an object there that I can use as a transporter. And like I said, we'll dissect these kinds of expressions a little bit later on. But for right now, just understand that it means that we're looking for something on our first center port to use as our transporter. So when that first flow item arrives now, the flow item will stay in the queue and wait for the operator to come and pick it up. And the operator knows that when the flow item arrives, that it needs to execute a set of tasks that says to travel to the queue, load the flow item, and then travel to the destination that the queue selected. Because the queue is still in charge of choosing which of those port connections to use. And then the operator is given a set of instructions that says, carry this flow item to this destination that I already selected for you. So the operator isn't making any choices here. It is just working as a supplement to the events that we saw on the queue already, where the queue is choosing which of those processors to send the flow items to. And now the operator is just being used to facilitate that movement. And so now there are additional delays in the model related to travel, where flow items might have to spend additional time in the queue as they wait for our operator to become available, because our operator now is a constraining resource.
So notice that the operator stays at the processor until it gets a command from the queue to do the next thing?
Correct.
Like in real life, the operator probably would go back until the queue has something and waiting, right? Rather than the process waiting at the processor that it's currently at before it comes back, would go back to the queue and then figure out which processor to send it to from there.
Right. Yeah.
Are there properties on the operator that define that to have it go back?
Mm-hmm. Yeah, because the assumption that we're making here is that when the task that says to drop the flow item off of the processor is done, we don't want to assume what the operator is supposed to do next. We kind of leave that in the user's hand to define those kinds of rules about like, okay, you just got done doing something. Now maybe go back to like a home base and wait for further instructions there, right? But like you correctly guessed, there are properties that allow you to indicate that kind of behavior. And there's a few different ways to do it. But the easiest way like for this model is to say, okay, this operator, and you can see there's all kinds of properties here about like how long it takes to load things and unload things and speed parameters. There's also a set of options that we call triggers. We'll talk more about triggers later on as well. But triggers are basically a way to say that when one of these events happens on the object, I want to assign some kind of custom behavior. And so there is a trigger on the task executor objects that is called onResourceAvailable. And the onResourceAvailable trigger fires whenever a task is complete. So whenever the operator finishes dropping something off of the processor, we will fire this trigger. And you can use that trigger as a way to say, when this event happens, I want you to travel to a home location. You can see it's a built-in option to that trigger because it's so common. You can either tell the operator to travel to an object location or to a specific XYZ coordinate. Either one of these would do what you want. But if you were to say travel home, then this means that the destination is defined as whatever I am center connected to as the operator. So that would be the queue in this case. And I would only do this if my task sequence queue, which we'll talk about what that means later on as well. If there are no pending requests for me to do, then that's when I do this. That's when I return home. So if I just choose that option and leave the defaults in there, then whenever the operator becomes available, she will always travel back to the queue and wait for further instructions there. And that'll help decrease some of the queuing time that we have, because now the operator is always waiting at the queue for the next thing, rather than saying, oh, now I got to walk back to the queue and pick it up, right? It's going to decrease our queuing times. So that's another set of options that objects have called triggers. And like I said, we'll explore this in a little bit more detail a little bit later on today. All right, any questions at all?
Just one more. Do we need a queue always in between a source and a processor?
Not necessarily. Not necessarily. You could have the source send to the processors directly, but the source only has the ability to hold one flow item inside of itself at a time. And so if you don't send things from a source to a queue like this, that might skew your arrival rates, because if there's nowhere, like if the processors were blocked, for example, and there was nowhere to send things, then that would prevent the creation of the next flow item if the flow item doesn't get removed from the source by the time the next flow item should have been created. You know what I mean?
Mm-hmm.
So it's not necessary, but I would consider it a good practice.
Okay, but we'll still be able to do the 65-35 and so on and so forth.
For sure.
From the source.
Yep.
Okay.
Mm-hmm. Yeah.
Got it.
Good. Any other questions? Okay, so let's take a 15-minute break. And when we come back, there's a couple of little details to review about what we talked about, and then I'll be able to give you your first model exercise to build on your own. Okay, is everyone back from break?
Yes.
Yes.
Yep. Okay. Now, like I said, there was a couple of things just out of the slides that I wanted to talk about, just kind of like wrap up our discussion on the objects. One of them is this idea of how every object is essentially a collection of events, right? And that's essentially what defines the behavior of an object, are the events that it knows how to execute. So this flow chart, this is an example of the system of events that is associated with a processor object. And so kind of imagine that every object has like this little flow chart behind the scenes that says that when a flow item arrives, this is what I start doing, all the way through to the end when it says, this is the end of what I do because now a flow item is gone. And then I'm just waiting for the next flow item to arrive, and that's when I kick off my chain of events again. So every object is a pre-packaged collection of events that produces a certain behavior. And so a lot of times the complexity of working with the object library is saying to yourself, well, if I want to have this behavior happen in my model, what object and what events of that object is going to give me the behavior that I'm looking for? The processor object is one of the more complex of those objects because it has a lot of events associated with it. Some objects have very few events, some objects have a lot of events. And so hopefully over the course of this week, you'll get exposed to enough of those core behaviors that you'll kind of get a feel for the different events that objects know how to do. Just a little bit more information also about ports. So remember that we have our input ports and our output ports that define the input relationship from an object, that how, say how you can receive flow items from other objects. Output relationship defines where you can send them. And the center connection allows you to involve an object like an operator in the events of an object like a queue. So we saw that with the example model that we were doing, where we saw that there was a way to say that we wanted to use a transport, and we took advantage of the center port connection as a way to request this particular operator to be part of the transport. Other objects like the processors have a very similar functionality. They also have use transport, but they also have other options like using an operator for the duration of the setup time or using an operator for the duration of the processing time that also uses the center port connection to request an operator to be involved in these events, just like an operator would be involved in this event. So the main difference between the different connection styles is the output input ports are for dictating flow item flow, and center port connections are for involving another object like the operator in the events of another object like the queue and the processor. The connection modes, we saw those from the drop-down menus. You can select your connection mode from the drop-down menu. One thing we didn't talk about was the disconnection modes. So I just want to go over that with you really quickly. If you make a connection that you decide that you don't want, there is a disconnection mode that is associated with the connection mode. So for example, there is a connection for the A-style connection, and then in the disconnection menu, there is a disconnection option associated with it that is called the queue mode. So like, for example, if I wanted to remove the connection from Q1 to processor 2, I would have to choose the queue mode, and then I click on the queue, and then I click on the processor to remove that connection. So removing connections is done the same way that you create them. You click on the origin object and then the destination object using the disconnection mode that corresponds with that connection mode. Now, in addition to the choosing of the mode from the drop-down menu, there are keyboard shortcuts that allow you to do that. So you can see here that for connecting outputs to inputs, you would use the A key or the A-style connection. To disconnect outputs to inputs, you would hold down the Q key or choose the Q mode disconnection from the menu. And then we have also the same keyboard shortcuts for center to center connections, either connection mode, which is the S mode, and the disconnect, which is the W mode. And they're just not named after the keys on the keyboard that you would hold down to put your cursor into the correct mode. Another common thing that comes up with port connections is needing to change the order of connections that you may already have without actually disconnecting them. The connections that are associated with an object is displayed in the properties panel. And you can even manipulate the connections from this set of properties if you wanted to. So for example, if I came back to this model, and if I remade that connection between the queue and processor 2, if you click on Q1, you can find the ports section of the properties. And then it will show you the different connection modes. Like right now it says for input ports, we have one input port on the queue that goes to the source. If you go to the drop-down menu, you can say that I want to look at my output ports, and it says, okay, you've got a connection to processor 1, and you've also got a connection to processor 2. And if you wanted to flip those so that processor 2 was the first outbound connection, you could highlight the processor 2 connection and then re-rank it. And now the first port will go to processor 2, and the second port will go to processor 1. You can see how they're now crisscrossed to point to the right object. And so that can be nice because you may create port connections and then change your mind about how they're supposed to be ordered. And this window, this interface is a nice way to be able to do that. You can also use this interface to remove connections, where if you highlight like the processor 2 connection and then click the red X, that will remove that connection from the object. Doesn't change what it says under send to port though, right? It still says that like some percent may still be trying to go to a port that no longer exists. So you got to watch out for that. But it is at least removing the connection so that the queue would not know that it has a second potential output object to send to. Okay, and then just also keep in mind the object properties we saw for manipulating the flow of flow items, where send to port defines the rule for where we want to send things, like choosing either port 1 or port 2 based on maybe a random selection or based on some other kind of a custom rule that you may assign. And then the use transport property allows us to activate the use of a task executor object to facilitate the transportation of flow items from the origin object to the destination object. Any questions there at all so far?
I believe this will come up later, Regan, just out of curiosity. We will be able to represent unplanned events, machine reliability, operator changes to schedule, raw material defects. Over.
Yeah, they're some of that is controlled by other objects that we haven't talked about yet. There's an object for defining like timetables and breakdown events, because they happen kind of independently. So they're kind of their own separate object. But like material defects, we'll see in this modeling example that we're going to do coming up, ways that you might model that as well.
Thank you.
Okay, so to this point, you guys have had to listen to me talk to establish kind of like the framework for everything else that we're going to do today. So hopefully in this next chapter, it starts to be a little bit more fun, because I'm going to introduce a couple of new ideas and give you guys a chance to build a model based on those new ideas. So this first modeling exercise is going to build one model, but we're going to take 5 phases to build it. So we're going to be building a little bit at a time, because that's actually a really good model building strategy just to begin with, where you take a large model that you know that you're going to build and you break it down into little like subsections and build a little bit at a time. That's a pretty good model building strategy in general, where you want to take kind of an incremental approach to building a model, where you build little parts of the model, test it, verify it, make sure it does what you want before moving on to the next part. And that's kind of what we're going to be reinforcing with this multiple phase approach to the model, that hopefully we'll drill this in a little bit over the course of the week, where you'll take this as a good strategy to employ, where you're going to say, okay, I know I need to build something that does this, so I'm going to build this little piece of it. I'm going to test it to make sure it works the way that I like before I move on to the next piece. And so this first exercise is going to take everything that we've talked about so far and add a new object to be familiar with, called the separator object. So pretty much everything we've talked about so far about using fixed resource objects, task executor objects, and port connections, that's all going to be in play with this example. But we're also going to introduce the displaying of statistics using our dashboard system, and also introducing the separator object, and see what the separator object can contribute to our models. So first thing with regards to the separator, first of all, you can consider the separator basically a processor with some special functionality, where it has all of the same events as a processor object. It has a setup time, it has a processing time, does everything the same way a processor does. But it also adds this extra ability to take a flow item and separate it in some way. And so the separation of a flow item can be handled in one of 2 ways. We can either say that a flow item is unpacked, or we can say that a flow item is split. Now, the unpack mode of the separator assumes that the flow item that it receives is a container flow item with other literal flow item objects inside of it. So that would be like a pallet that has other products packed inside of it. This is something that we haven't seen yet, but we will a little bit later on. The other way that you can separate a flow item is to say that the flow item that's received by the separator is just going to be copied a certain number of times based on a quantity that you can dictate. So in our example model that we're going to build, we're going to be using the split mode, and we'll come back around and see how the unpack mode is different when we talk about flow items that are acting as containers for other flow items. But for right now, we're going to create a flow item that gets sent to the separator, and then the separator will clone that flow item a certain number of times. And the number of flow item clones to create will be governed by what's called the quantity field. This is an object property where you can dictate a value, either given by a literal value, or it also accepts an expression value. So if you want to create like a random number of clones, you could do that as well. But whatever value you put into the quantity field is what determines how many flow items are released by the separator. So in split mode, a single flow item goes to the separator, and then the quantity dictates how many flow items will be released by the separator. So it's a way to take one flow item and turn it into many flow items. Does that make sense?
Yes.
Now, the other new thing that we want to do here is the displaying of output data, statistics data. Now, we already saw how every object keeps track of some basic stats about themselves using their stats window on their property panel. In addition to that, we can also create what we call dashboard charts that are displayed in real time with the model's execution. So a simple way to do that would be to highlight an object whose stats you want to report. And then there is a thumbtack icon associated with each of the stats that the object reports. And if you click on this thumbtack button, it gives you the option to add that statistic as a chart to a dashboard. And that will automatically open one of our dashboard windows, and it will create a chart that looks like this on the dashboard for you automatically. And that means that you'll always have access to the object stats, even if you're not clicked on that object. You can always just display it by looking at the dashboard chart. And this will be our first introduction to using the dashboard system. As we go through the week, we will see some different ways that the dashboard system can report from very simple statistics, like what we're going to do here, to even more complex customized statistics using some other tools in the software that we'll talk about probably on like Wednesday or Thursday. Okay, so just to kind of illustrate what we're going to do with the model, you're going to want to create a new model. This is going to be a completely different setup. The default units are fine. You can use seconds and meters if you want to, but if you also want to experiment with some of these different units and how that affects your model, excuse me, that's fine as well. You can go ahead and do that. And then in our model, what we want to do is create a model that looks like this. So we'll have a source that feeds into a separator, that then feeds into a queue, and then to a processor, and then a sink. And then also notice our operator with center port connections between the queue and the processor. And so we want to describe a system that says every 120 seconds, a flow item will be created, and that flow item will represent a shipment of parts. And each shipment is made up of 4 individual parts that need to be split by the separator. So our one flow item that we create every 120 seconds actually is going to represent many flow items. And so we'll use the separator's capability to turn that one flow item into 4 flow items, which represents the split out quantity. So kind of imagine like you're receiving like a box full of parts, and the separator is opening the box and giving you the individual parts, right? And we'll use the split functionality to accomplish this. And so when the separator splits out its flow items, it'll put all the flow items into the queue. And then the flow items in the queue need to be processed one at a time. And we're going to say that every flow item is going to go through a 3-second setup time, followed by a 10-second process time. And that'll be handled by the processor's properties. And then our operator will be responsible for transporting flow items from the queue to the processor, and also from the processor to the sink. And then we also want the operator to be involved as part of the setup time at the processor. So we want to involve our operator in the events for transporting from the queue to the processor. We want to involve the operator in the event for transporting from the processor to the sink. And we also want to involve the operator in the setup time of the processor. And then we want to create some dashboard charts. We want to look at the content history over time of the flow items as they wait to be processed. And we also want to know the throughput of all of our processed parts. So you can look at the content history by looking at the content stat of the queue, and we can get the throughput by looking at the input statistic of the same. So create dashboard charts for those using that thumbtack option that we talked about on this slide. Okay, any questions at all? So take a few minutes to work on that. If you have any questions, go ahead and let me know. And then this will probably take between about 5 and 10 minutes, thereabouts. And then we'll do a walkthrough and kind of talk about some different choices that you might make along the way. All right, good luck.
Hey, Reagan, how do I make my separator do quantity 4? I have her to separate mode split, and then I'm stuck.
Yeah, so in addition to choosing the split mode, there's also the quantity value that you can input below that, and that'll tell the separator how many to make. So like if you look at the properties of the separator.
I didn't realize I could just write it in. I was using the drop down.
Yeah, you can just type any field input field like that. You can either choose a pre-programmed option if you need to do something fairly complex, or you can just type in the value directly.
Cool, thanks.
Yep.
Sir, can you remind me how to associate the operator requirement to transport from the queue to the processor?
Yeah, so that'll be handled by the queue properties. In the output section, you'll click the box that says use transport. And then you'll want to make sure that you've mimicked the port connections as shown on this slide to make sure that there's a center port connection from the queue to the operator so that the operator can be properly requested.
Excellent.
Are we assuming that there's no split time or a process time for splitting?
Yeah, that's a good question. So if you had a processing time on the separator, that is essentially assuming that there is some duration of time that it takes to turn the one flow item into many. So if you were to put in a process time of 0, the one thing that's created by the source is immediately turned into 4 things in no amount of time, which is effectively making it like as if the source had created 4 things. You know what I mean?
Yep.
That's a good question. Okay, so is everyone ready for the walkthrough then?
Yeah, sure.
Yep. So like I said, starting with a blank slate model, just starting by creating the objects. And this is always a good first step when building a model, is to think about, what objects am I going to need in a model like this? In this exercise, it kind of feels like cheating because I've already told you what objects you kind of need. But in a real life model, you might need to consider, well, what are the behaviors that I need to get out of this model? And what objects might best represent that behavior? Just so that we can get things put together. And so once you have your objects out there and you kind of laid them out in the way that you want, then I recommend going ahead and making your port connections. And so I'm going to make a connection from the source to the separator to the queue, to the processor, to the sink. And that's where things start. And then I need center port connections from the queue to the operator and also to the processor. So now I have, this is kind of a new thing that we're seeing. We didn't see this in the example where 2 objects potentially are going to be requesting the operator. And that's fine, right? Just using these port connections allows the processor to know about the operator and potentially use it. Same thing with the queue. So after I've laid out my objects and I have created my connections, the next thing to do is to change any object properties that I know I need to change. And so in my source, I know I need to change the inter-arrival time so that my arrival rate is every 120 seconds. And so since my model is already set up with its native unit to be seconds, then I can just type in the 120 there to make sure that that we have this in 120 seconds. And then on my separator, I need to change my separation mode to the split mode. And then for my quantity, I can just type in the number 4. Again, in these sorts of input fields, I can just input a value directly, and this will tell the separator to always create 4 flow items out of the 1 flow item that it receives. Now, like what was asked earlier about how much time this split event should take, if you leave the processing time at 10, that means that the flow item will arrive, it will be delayed 10 seconds, and then after that delay, the 4 flow items will be created and placed into the queue. So it's kind of up to you to decide whether or not you care about this amount of time. Might make sense, though, to say that the process time is 0, so that the one thing is immediately turned into the four things with no delays associated with it. So that's what I'm going to do in my model. I'm going to set the processing time to 0. Now the queue doesn't have very many properties that we need to change. We just need to be able to come to the output section and say use transport, and that will allow the operator to be requested. And then on my processor, I need to put in my setup time of 3 seconds. My process time is already set correctly, but I do need to check the box that says use my operator for the duration of my setup time. So that means that while the operator is doing setup, or rather while the processor is doing setup, the operator has to be present during that event. And then the last thing that we need to change on the processor is to say use transport for send to port, so that the operator can be requested when it's time to send something downstream. And so if we run it and see what we've got, the 120 seconds goes by, and that immediately puts 4 flow items into the queue. And our operator starts working by carrying them to the processor as the processor becomes available, and then carrying them out to the sink. And so just as he finishes the last flow item in that split quantity, we should see the next batch arrive pretty shortly after that. And there they are, where the next set arrives and he starts working on those. So this is where it might be interesting to see the change in the contents of this queue, to see the arrival of like the first set of parts and how quickly you can work through them, the second set of parts and how quickly we can work through them. So I'm going to reset my model and go to my queue. And under the statistics properties, I am going to choose to display the content stat by going to the thumbtack and say that I want to pin to the dashboard a content versus time chart. And that opens up this little dashboard window with that chart. And you can resize the chart, move the chart around. And if we just hit reset and run again, the chart data will populate. When 4 things arrive into the queue's content immediately jumps to 4. And then every time the operator takes something out of the queue, we reduce the content by 1. And we're seeing this change in the content over time. And so as we work down to 0, we can see that there's a little bit of time spent where the queue is at 0 content, and then the next group of 4 arrives, work our way back down to 0, and the next group of 4 arrives, we work our way back down to 0. So again, just viewing the history of changes to the content stat of the queue. So this tells me essentially how long flow items are staying in the queue. I can see like how many there are and how long it takes to get down to 0, and when the next batch arrives, how we get down to 0. And if I wanted to know how many total flow items have been processed by the system, I could go to the sink object, look at the statistics for the sink, and say that I want to get a throughput-based stat by again going to the thumbtack. And this time, instead of saying I'm going to pin to a new dashboard, I'm going to pin this to my existing dashboard. And then it gives me some options. And I'm just going to choose the first one where it says I want to show the throughput of the sink. And it just tells me that the sink has received 45, now 46 flow items. So this is a common way that a sink will get used, where we use its input statistic to display essentially the throughput of the entire system. And that works fine as long as you only have one sink. There might be times though when you have different, multiple sink objects, you could send everything to the same sink like we're doing here. But in more complex models, especially if there's a different kind of stat you want to display, you might have multiple sink objects. And you may want to display different throughputs for different parts of the model using different sinks. But this is an example of using a sink in a fairly common way, where its throughput is telling us the throughput of the entire system.
One question. So the second thing we're supposed to get is what is the throughput of the process parts? Where do we see that?
That's on. I did this by going to the sync object and then choosing the throughput options on the sync statistics. I just said I want to pin the throughput to the dashboard, and that gives me this chart.
Okay.
Notice though that the sync doesn't have output, right? Because output of an object would be flow items released by the sync, but the sync just receives things and destroys them, so it doesn't actually have an output statistic. It only has an input statistic. Okay, so go ahead and save this model. We're going to be coming back to it for the rest of today and part of tomorrow. So in the next section, we're going to be talking about a really important aspect of working with simulation, and we're going to kind of weave this into our phase 2 example model, where we want to talk about randomness and how randomness is an important part of building a simulation model, accounting for randomness, accounting for variations. And we'll talk about that within the context of using statistical distributions as inputs to a lot of our object properties. And we're also going to introduce an important FlexSim concept that we call labels, which is a mechanism that we provide to easily store and access important information that your model needs to be aware of while the model runs. So the first thing we're going to spend a little bit of time talking about is randomness, because like I said, it's a really important idea to grasp for simulation just in general. And you might have noticed while we were running that model that the inputs were always pretty static. They were always, the model was pretty much behaving the same way every time. Like if we watch the model run for a little while, we'll just speed it up. Like you take a look at something like the content history, where we always go up to our 4 and then we get down to 0, up to 4, down to 0, up to 4, down to 0. And this content versus time graph is looking pretty deterministic because there's no variability at all related to how often our shipment arrives, how many parts are in the shipment, how long it takes to process the individual components in the shipment. The model is behaving in a very, very deterministic way. And for a lot of models, that's not going to end up being something that's pretty realistic. We need to account for variations that our static values don't properly account for. We need to be able to handle variability that exists in the time that it takes to do things and how many things there potentially might be. And we use statistical distributions to allow us to account for that. And in fact, using distributions in this way is a form of abstraction, where we use distributions as a way to say we don't really care why there's variability. We just want to properly account for variability in such a way that our model doesn't just behave exactly the same way every single time. And so consider the question about how long does it take to do something. So consider that you might have like some kind of a process or procedure that exists in your real world system. You were to ask someone, hey, how long does it take you to do this? And they might say, well, it takes about 10 minutes. But what does about mean? The fact that they're saying that it takes some about amount of time, that it's not like an exact amount of time, that implies that there's some kind of variation, some sort of variability associated with the time it takes to do something. But what does that variability look like, and how do you properly account for it mathematically? So here I have example graphs for 3 different kinds of statistical distributions, where each of these distributions has nearly the same mean. They have nearly the same about some value. But if you were to look at something like the exponential distribution that has a mean value of 10, and let's just say that this 10 represents 10 minutes, like the first bullet point says, the distribution of those values along the x-axis gives us a different picture of what that variability might represent compared to something like the triangular distribution in the middle, or the log normal distribution on the right hand side. All 3 of these distributions might produce an average value of 10, but the way those values are distributed is very, very different. And so choosing a distribution that properly accounts for the variability goes way beyond just needing to account for the right mean. but also needs to account for the right proportions of values and the right shape of the curve that a set of values might look like. So like, for example, like I said, exponential distribution compared against something like the triangular distribution, though they may have the same mean, the distribution of those values is very different, where like the triangular distribution has most of its values between about 8 and 12, and the exponential distribution has most of its values between 0 and 10. And so the kinds of information, the kinds of values you could potentially get from these different distributions could be wildly different, even though their means are the same. And so we want to account for the different shapes of these graphs so that we properly represent what about means. And so different distributions have different basic shapes like these three examples, but then they also take different parameters that dictate how the values are distributed along the x-axis value. So when using a distribution as part of an object property, usually all you have to really worry about is choosing the distribution from a drop-down menu and then inputting the proper parameters so that the values are distributed on the x-axis the way that you want. Now, a lot of times the question then becomes, well, how do I know what distribution to even choose to begin with? In a real world project, in a real model, the types of distributions that you'll use and the parameters that you need to input to make the graphs draw correctly will be dictated to you by data gathering. So hopefully what you'll do is you'll gather a bunch of data about the way various processes and various aspects of your system are going to work, and you'll perform what's called a curve fit to be able to associate your real world collected data with a distribution with a given set of parameters in order to properly account for that variability. Sometimes you could also use what's called an empirical distribution, which we'll take a look at a little bit later on, as a way to take, again, that real world data and cause your model to use that data as customized distribution so that your real world data, again, is properly represented in the object parameters, the object properties that you have in your model. Okay, so like, for example, let's say that we wanted to use the distribution to change the arrival rate of something like our source. So like I said, if you look at the source objects, the arrival rate right now says that we're going to get a new flow item that represents a shipment of flow items every 120 seconds. But what if there is some variability associated with that? What if there is some randomness associated with this arrival rate that we want to account for? That means that rather than just typing in a value like 120, you might go to the drop-down menu, go to where it says statistical distribution, and choose one of these distributions that we can implement as part of this object property. Now, for arrival rates, as it happens, the exponential distribution is really, really good at modeling random arrivals. There have been a lot of studies and papers written on this. I won't get into it here, but the main thing is like the exponential distribution just does a really good job of modeling random arrivals. It doesn't really matter what you're talking about, whether it's like material under the assembly line or customers into a store, it really doesn't seem to matter. And so this, again, is an application of abstraction, because if we say that the arrival is based on the exponential distribution, that implies that there is some reason why things show up on this random interval of time, but we don't care what that random interval of time represents. We don't care that it's random because there's different like shipping schedules and arriving schedules or anything like that. We just care that things arrive based on this curve, so that most of our values arrive at this end of the curve, but we have some outliers way out at this end of the curve. And then we specify what the mean value is by changing the scale parameter to this distribution. So for example, if I say the exponential distribution has a location of 0 and a scale of 120, the basic shape of the curve stays the same, but the x-axis values have now changed to be more in line with what our parameters say they should be. So with a location value of 0, that means for the exponential distribution that the minimum value that we can get on this curve is 0. You could have an arrival interval of 0 time, or it could be as much as over 500. And again, remember that this is in terms of number of time units. So that would mean that the time between the creation of flow items in this case could be anywhere between 0 and way out here, probably closer to even 600. But because of the histogram bars, we can tell that some values are more likely to happen than others. Taller bars indicate a higher probability of an interval in that range of values. Anytime that we choose an option from our drop-down menu, like here where we chose our distribution, if you want to see that that drop-down menu that shows you the nice histogram bars of that distribution, rather than going to the drop-down triangle and choosing from this menu again, I want you to note this button that's right next to the drop-down triangle that allows us to edit the input parameters for this property. So if you click on that button, that pops down the window again. It says, okay, in here you've already selected the exponential distribution with location 0, scale 120. But if you were to choose something from the drop-down menu, this would be choosing a brand new option that would overwrite what we already had there. So notice now I chose that from the menu. And now it says that we have an exponential distribution with a location of 0 and a scale of 120, or excuse me, a scale of 10, because I chose from the drop-down menu, which obliterates what I had in there before. So I'd actually have to come back and edit the value. So if you are wanting to choose a new option, go to the drop-down triangle. If you want to edit the existing option, click on the edit button to pop open this window and see what it says.
So I'm sure you already said this. What is location? What can you change in that, and what does that do?
Yeah. So the location parameter for the exponential distribution essentially defines the floor of this distribution. So that would mean that your range of possible values from this distribution is between 0 and up to whatever the shortest histogram bar on the chart is. But the scale would tell you what the mean is for this distribution. And so generally speaking, you can kind of think of the location value as like the minimum value that this kind of a distribution can give you. But the maximum is not defined. It's given by the shape of the curve. You can see it's like way out here in like the 600 range.
So if I plugged in like 300 as a location value, that histogram would just cut off there.
Yeah, if you put in like 300, then what it does is it means that you now have a mean of 420, which is the location plus the scale, right? Because now the minimum value is at 300, and then we have the exponential curve beyond that point.
Okay, got it.
Because you've now shifted the curve down the x-axis by the location amount. Now, a big part of what we're going to do in this phase is going to be substituting our static parameters with some distribution values. Another thing that we want to go over in this model, it's kind of a new idea, is this concept of creating labels. So this is a very FlexSim specific idea, where in FlexSim, we don't assume that things have like model specific or industry specific like attribute data that we want to be able to represent. An example that I like to use for this is the notion of weight. If you consider that, like, if you were to build a model where part of your model behavior, part of your model logic depends on knowing how much things in the system might weigh. Like imagine you're Amazon or something like that. You're trying to, boxes that have certain weights so that you know like what their shipping shipping costs should be for non-prime people, or like how many of those boxes you can safely load into a truck. The weight of things might have an impact on the way your model behaves. That being the case, though, FlexSim doesn't have an innate notion of a weight attribute. Like we don't know like how much flow items are meant to weigh, because that's not something that every model is going to need. And so generally speaking, if it's not something that the majority of models are going to need to be able to take advantage of, we don't include it as like a built-in feature. So what we did instead is, rather than putting a weight attribute on everything that you have to be concerned with, whether you want to use it or not, what we did instead is we created a mechanism called labels. And labels then becomes the way that we want to store important information about model behavior, or about statistics information that we want to gather from a model, so that you can say that this label represents this important piece of information that my model needs to know about. So rather than having a built-in weight attribute or weight property of an object, we instead say, here are some labels, name it weight, and then assign a value to it that represents the amount of weight that this thing now represents. So we do the same thing with things like cost. We don't have like a built-in costing mechanism. You use labels that indicate like how much things cost, or other kinds of information like that. So labels end up being very important because they can have an influence on the way your model behaves. They can have an influence on the kinds of stats that you can gather, and they become a mechanism that is very, very commonly used in just about every model that I've ever built or been a part of. So it's important when using labels to keep in mind that at the core, it is a data storage and accessing mechanism. If there's any sort of information that is important to your model that the model doesn't already have a way to manage, then you're probably going to need to use a label to manage that information for you. Okay. Now, when using a label or labels on an object, there are a couple of key important informations to be aware of. First, and probably most important, is the owner of the label. Since in FlexSim, just about anything can have label data assigned to it, whether you're talking about objects or flow items, or pretty much any entity in the software can have a set of labels assigned to it. It's important to understand that labels should be assigned to something that they are related to. So again, consider a flow item that represents a package in the system, and we want to know how much it weighs. It makes sense to assign the label that indicates that package's weight on the package itself, because FlexSim is a very object-oriented environment, which means that we like individual objects to be in charge of the data that belongs to them. And so when you establish an owner of a label, you're basically saying who is in charge of managing this data. Who does it make sense to have be in charge of this piece of information? So it might make sense to assign data like that to a flow item. It might make sense to assign data like that to an object, because it all depends on who's in charge of managing the data. And so as the modeler, when you work with labels, that's one of the first choices you'll need to make, is to say, to whom am I going to assign this label data? And the next choice you'll have to make is to give your label a name. Now, label names can be whatever you want. Like in the case of a label that indicates the weight of a package, it might make sense to call the label weight, because that way it's actually a descriptive name that says that this data represents the weight of this thing in the real world. Now, since you can give labels whatever name you want, it's very, very flexible. One thing I would be careful of, though, is don't give your labels names that are too vague, right? Like label 1 or label 2 or something like that. It should be descriptive and tell you something about what that label's job is, like what kind of information it keeps track of, what kind of values are possible, and what kind of an impact it might have on your model. There's some additional naming best practices that we'll go over. The first most important naming best practice, like I said, is to give it a descriptive name. One of the other really big naming conventions that I'll recommend is to start label names with an uppercase letter. And that'll become clearer as we kind of go through the week, as we use more and more labels, because we'll be using labels constantly in all of the projects that we build this week. And we'll talk about why some of these naming conventions are important as we come across them. But descriptive name is number one best practice. The second best practice that I would recommend is to start label names with an uppercase character. And then the third thing that you need to be aware of working with a label is the data that is actually being stored by the label. So remember again that if we're dealing with a label that represents the weight of a package, or maybe the serial number of a part, or the SKU number of a component, then it makes sense to say that this label is assigned to the thing that's in charge of that data. We give it a name like SKU or weight or serial number. And then we need an actual piece of data that represents that serial number or that SKU number or that package weight. And so there has to be some kind of value that is assigned to indicate what information is stored by that label. So like, for example, on this next slide, you'll see that this is a flow item that has some labels assigned to it. There is a label that has been named type that maybe is some kind of a categorical value that tells you what kind of thing this flow item represents. And you can see that it has a value of 5 assigned to it. A very simple numeric value, it's very common, where you might just use some kind of a simple categorical ID number that says this is type 5 or this is type 2. But for other more complex ideas, you might use things like text, like to say that this thing's serial number is the value XYZ123. And there might be a lot of different flow items that have different types. You might have things that are type 1, things that are type 2, things that are type 3, things that have different serial numbers, where you might have different values stored in the label with this serial number name. So here we have, for example, a label called type that has who knows how many different possible values. This one just happens to be 5. Here we have a label named serial number that has this particular value, XYZ123, with who knows how many other possible values there might be. And so the label name, again, is telling us what the data represents. And then the actual information to the right of the name is telling us what information is actually stored in that label. Okay, does that make sense? Does anyone have any questions there at all?
Are we going to go over each type number and what they mean?
How do you mean?
Well,
like the different values?
Yeah, what does that value mean? The type 5, what's a type 4 and what's a type 6? Like,
yeah, well, that's up to you, right? Because these are labels, these are things that you have control over naming, you have control over what these values represent to you.
Okay, I see.
A really common thing to use a label like type, though, is to say, well, here's type number 1 thing with maybe some set of attributes, and here's type number 2 thing. It's just kind of an abstract way of categorizing different kinds of things, but it doesn't have to be type, right? You could call it kind, you could call it SKU, you could call it anything. It doesn't really matter what, as long as you know what it means and the values that you assign make sense for how you're using it.
Okay.
Yeah, labels are something that's completely in the hands of the user to decide whatever meaning you want those labels to have. And
so can you then reference this data in like your other expressions? Because I see you got like operator 1 here. So you can say when you're running type 5, it can only be used by operator 1 as long as it also matches this SKU or something like that.
Yeah, exactly. Yeah, that's the whole reason why we have these label values, is so that you can use the information being carried, in this case, by like a flow item, and say, oh, hey, when I need to be processed by a processor, the operator that has to come and be part of my process must be operator 1, because now that's assigned as a label. So now I would say, find my operator by looking at my label called my operator and using whatever information you find there. Yeah, it's a good example of that. And that's one of the big reasons why we like to use labels, is because the data being carried by these labels can influence model behavior in StatsGAP.
So even type, serial number, my operator SKUs, all those are also user specific, or however you want to define
Absolutely.
that option. Yeah. And then you can then reference those in relation to something else in the model. That gives you a lot of flexibility.
Tons. Yeah, because by default, there are no labels really assigned to anything. It's a completely open field to name them how you want, assign them the data that makes sense for you, and to access them at any point in the flow of your model's logic. And not only do they influence the way your model behaves, but they can also have an effect on the way your model can report on outputs of interest, on your statistics. We'll see an example of that in this model as well. So that's kind of laying the groundwork for labels, but how do you actually go about creating and using these labels? Well, oftentimes assigning a label value happens at the same time as some event in your model. And so typically that means that during different events, like for example, these trigger events that we kind of introduced a minute ago, but we're going to go into in more detail later on, where you might say, when this event of the object happens, like during the on-exit event, I want to set a label on my item called type, and then I want to assign it some value according to some pattern. Like maybe you use a distribution, or maybe you have some other expression that you want to put in there that says that the type maybe is read from an Excel sheet, or maybe the type is just randomly assigned like it's doing here. It just kind of depends on what your model needs to be able to do. And so during these trigger events, there are options that allow you to both read from and write to labels that exist either on flow items or on other objects. And they give you a way to assign these labels when a particular event takes place. Because like I said, oftentimes that's what kind of triggers the assignment of a label. We would say, where this event happens, assign this label with this name, with this value to some object. And so not only can we assign the label values, but then we can use those label values as a way to help gather and display statistics. So in the dashboard template library, this is a library of options that comes up when you have a dashboard window. So like, for example, if I were to come back to my model, click on my dashboard window, my library is now changed to be a set of options that can be placed into the dashboard instead of the grid. So like if you click back on the grid, I've got my object library again. But if I click on the dashboard, I have my dashboard template library. And from here, I can drag out pre-built charts that know how to work with things like labels. Like any of these charts that say by type should really say by label, because it's assuming that there is some label on the flow items that we're gathering stats about as they flow through this model. And we want to separate out the statistics by label values that they carry with them. And so on the slide, it's basically saying, like, if you were to choose something like output by type, you could create a chart that then says that the label that's being carried by the flow items, and it could be the type label that we have in there by default, or it could be any other label that you assign, and that could influence the way these statistics are drawn on the chart. Like I said, we'll do an example of that together in a minute, but just kind of introducing some of the basic ideas of a label for right now. Okay, any questions at all so far? Okay, so let's get some practice with changing over from our static object inputs and use some distributions instead. So we're going to say that our arrival rate of our model is now being described using the exponential distribution with a location of 0 and a scale of 120 instead of the static 120. We're also going to change the number of parts that come out of the separator. Instead of being a static 4, we're going to use a distribution called D-uniform with a minimum value of 2 and a maximum value of 6. And so the D-uniform distribution says that you can return any integer value between the minimum and the maximum. And because we're going to put that into the quantity field of the separator, that's going to tell us how many flow items are going to be created by the separator. We're also going to alter our setup time on the processor to be using the triangular distribution, which takes a minimum value, a maximum value, and a most common or mode value. And we're going to set those to be 1.5 by 4.5, 2.5. We're also going to adjust our processing time of the processor to use the log normal distribution. Now, the log normal distribution has 3 different ways of being described, and you're going to use the one that takes the mean and the standard deviation as the inputs. So the other 2 take different inputs, so make sure you choose the one that indicates the mean standard deviation as the input parameters to the distribution. And we want those to be a mean of 10 and a standard deviation of 3. Now, another way that we're going to use randomness is we're going to say that there is a 20% chance that parts need to be reworked after processing and be sent back to our queue. So if you look at the layout slide, you'll notice that there is now a second output port on the processor, and we want to use that second output port 20% of the time, and we want to use that first output to the sink 80% of the time. So that means that you'll need to adjust the send to port of the processor to use port 1 80% of the time and port 2 20% of the time, which will allow our flow item to be carried back to the queue by our operator and await a rework chance. So this is like an example of like maybe this processor is like a test bench, and 20% of parts fail and need to come back and be reworked. And this is a way that you might account for that by changing the rework or changing the output port used to some randomly selected port according to some percentage of the time like this. It's a fairly simple way of doing it, but it's a fairly common way of doing it. And once you've got the main model description built, those 5 bullet points, then we'll talk about how to get this output rate, or how to get this output statistic by looking at the throughput of our processor according to the rework state of the flow item. So we want to know how many flow items left the processor that were good parts versus how many needed to be reworked. And we'll use labels to accomplish that. So if you want to give that a try on your own, you're welcome to, but I was intending to make that part of the walkthrough anyway, so that we can see how that might be done. Okay, any questions at all on what we're going for in phase 2?
Can I clarify the number of parts in a shipment, the D uniform min 2 max 6, is that out of the processor, or I'm sorry, the separator, or is that out of the source?
That's the separator, yeah. So where the separator right now is saying that it will create 4 flow items every time, we want to change that to a distribution so that we get a random number of boxes created by the separator.
Okay.
All right, take a few minutes to give that a try. If you have any questions, go ahead and let me know. I would expect this to be probably about 10 minutes, more or less. So if you get stuck along the way, let me know, and then we'll just plan on doing the walkthrough once everyone's had a chance to give it a try. All right, well, we'll move over to the walkthrough then for the main part of the description. So just going to come back over to the model, and adding in the distributions hopefully didn't feel too strange, because it's really similar to what we did in the first phase, where we went to each object and changed their parameters, changed the inputs. So in this case, I've already done the source because it was part of the example where we were talking about distributions and adding them to the properties of an object. And so just make sure that we said that during the inter-arrival event, we wanted to define the arrival rate by using the exponential distribution with a location of 0 and a scale of 120. As we move on to the separator, we just need to change the quantity field. So remember that where you put the distribution impacts the way the object is going to behave using that distribution. So if you were to take the distribution that we need for the quantity, this D uniform with a minimum 2, maximum of 6, and put it somewhere like the setup time or the process time, well, it's not going to tell us how many flow items we're going to create anymore. It tells us how long one of these times is going to take. So we want to make sure that we go to the quantity field and say that we're using a distribution. We'll choose D uniform from the list, and again, say that our minimum value is 2 and our max value is 6. So now for any given flow item that goes into the separator, we don't know how many flow items are going to come out. It might be 2, might be 3, 4, 5, 6. It just depends on how things work out on rolling the dice, essentially, on this distribution. And then on the processor, we also needed to change our setup time so that it's not a flat 3 seconds anymore. We're going to say that this is given from the triangular distribution with a minimum of 1.5, a maximum of 4.5, and a mode of 2.5. Now, one thing to kind of note, one of the reasons why I chose the triangular distribution for this particular example is the triangular distribution is a handy distribution to know about because it only requires 3 input values, this min, max, and most common. And that can be useful in the early stages of a model where you haven't done the data gathering yet to find out like what true distribution a particular object property might fit into, but you know, like min, max, and most common. Those are 3 usually pretty easy data points to get. imagine yourself talking to someone, say, hey, how long does it take you to do this? They say, well, fastest case 1.5, slowest case 4.5, but usually about 2.5. And that draws a curve that looks like this, that is triangular, using the minimum value as one bottom end of the triangle, the maximum is the other bottom end of the triangle, and then the mode as the peak of the triangle, and all the other values distribute off of based on that. And so triangular is a useful distribution to use in the absence of good data, where you can kind of get a ballpark estimate of the variability without having to do a lot of work to find out how to construct that distribution. So a lot of people use that sometimes as like a simple way of introducing variability, or as a placeholder for a distribution that you're working on gathering data for at a later time. But so that you don't have to be limited to just like a single value like 3. You can still get some variability and get a feel for your model that way without having to do like a full-on time study yet. So a lot of people use it in that way. For the processing time, we were just needing to use the log normal distribution that uses the mean standard deviation as the inputs. So again, notice, like I said, there are 3 different ways of constructing a log normal curve because it's a fairly common one. So we give you some different options. And the log normal mean standard deviation only needs you to provide a mean value and a standard deviation value, and it will do the rest. So again, kind of a good one to use in the absence of hard data in like a true curve fit that you want to maybe do down the road. Because again, it takes just 2 simple parameters that are pretty easy to input compared to like log normal 2, which wants a location, a scale, and a shape. And unless you're like super familiar with statistics, it may not be totally clear how these 3 parameters work together to draw a particular curve. Because these would be parameters that would be given to you by a proper curve fitting. But if you just choose something like log normal mean standard deviation, it gives you the basic curve shape of a log normal curve, and then you just have to put in a mean and a standard deviation. These are usually pretty easy ones to guesstimate. Okay, anyone have any issues with the distributions, the distribution portion of this? Okay, so on the kind of the last bullet point here was to get this this rework loop put into the model, where there's a 20% chance that parts need to get sent back to the queue and be processed again. Easiest way to do that is to, first of all, make the port connection that we need. So I'm going to hold down my A key and make a connection from the processor that goes back to the queue. So that now gives me the option that says that if you can't use port number 1 for whatever reason, then you can use port number 2. But if you look at the processor under its output properties where it says send to port, notice that it still says that it's assuming to use the first available port. Now, because the sync object is essentially a black hole, it's always ready to receive. There isn't ever a condition with the way things are set up right now where flow items will need to be reworked. So we have to choose a rule on send to port that says some percent of the time you need to use this other port connection. So the easiest way, again, to do this is to say that we will choose a random port by percentage, and we'll say that 80% of my flow items go to port number 1, and 20% of my flow items go to port number 2, keeping in mind that this option isn't smart enough to know that we have 2 port connections, 80% chance to go to port 1, so therefore everything else must go to port 2. It wants you to be more explicit than that, so I need to make sure to put in both the percentage and the port number associated with that percentage, and the leftover percentage and the port number associated with that percentage to get the proper 80-20 split that we're looking for out of the process. Okay, so let's test it to see what we've got. If we hit reset and run, now we have a long time to wait before our first flow item arrives. And when it does, actually, let me start that over again because I went too fast. So notice that 2 flow items came out of the separator. So we created the minimum number of flow items that we could get based on the quantity field that we had set on the separator. And so here's a flow item that needs to go back and get reworked. Goes back again. And you can see what this is doing to our content versus time. You can see how something leaves and then comes back leaves and then comes back with these little blips on the chart. And because this is a 20% chance, this one part has actually been reworked, it looks like 5 times so far before it finally goes out to the sink. And that's fine because we don't have any additional controls in the model that say like, well, maybe you're only allowed 2 chances at rework before it's just like thrown away or something like that. With the way this is currently set up, it just says that everything has a 20% chance to be reworked. And every roll of the dice is a fresh roll of the dice. It doesn't depend on the results that we got before. So even though it was only a 20% chance, we had 5 reworks on one part, which is just bad luck using this kind of a simple distribution of values. And for now, that's fine.
And no matter how many times you run the simulation, you'll get these same results, right? Because even though it's quote unquote random, the simulation still runs the same numbers every time.
Only because the statistics option that says repeat random number streams is checked.
Okay. Got
if we were to uncheck that and reset the model, we could get a completely different set of random numbers.
Okay.
And we'll talk about why that's important to be able to get different random numbers a little bit later on tomorrow. But yeah, for right now, the model is going to run exactly the same way with the same set of random numbers every time, which just makes it easier to verify that the model is working correctly because everything's going to happen the same way. But if we were to turn that off and hit reset, then we get a completely different set of results. And so again, you can kind of see what this is doing to our content versus time, where we got a shipment that had, it looks like 5 flow items, and then we worked our way down. And there's a little rework blip there in the chart before we finally get down to 0. And what's kind of interesting about this is that if you look at the throughput of this model, it says that 7 things have gone to the sink. And if you look at the processor, though, the processor stats says that it has sent out 14 things. So why has the processor sent out 14 things and the sink has only received 7 things?
Is that the rework?
Yeah, it's because of the rework, right? Because the output of the processor could be to either of its 2 port connections. So some things went to the sink, but some things went back to the queue. So the processor thinks, okay, I've sent out 14 things have left. And the sink says, well, I've only received 7 things. So somewhere in there, there are 7 things that needed to be reworked, right? Because the number of things released by the processor is not necessarily the same number of things received by the sink because we have multiple port connections that we have to account for. So how can we create a chart then where we can know of those, and actually let me just stop it right here, of the 15 things that the processor has sent out, how do I know how many of them are rework versus how many of them are good parts? Well, right now I have to kind of extrapolate that by saying, okay, the output is 15, the input to the sink is 8, therefore that means 7 of those 15 must have been rework. But that's a lot of work for me to have to do. Wouldn't it be nice if there was a chart that just displayed that for me? Well, I can do that with the aid of labels, right? Because right now, when flow items leave the processor, I don't know the difference between something that goes to the sink versus something that goes back to the queue. So in order for me to gather a statistic about the processor's output, I need to know the difference between things that, processed normally and just got sent to the sink and things that had to go back for rework. I need to create a category of things that go to the sink and another category of things that go back to the queue. And this is one of the reasons why you might use a label, because I can use that categorical value as a differentiating factor for the gathering and the displaying of statistics. So the first thing I need to overcome is knowing the difference between something that leaves the processor on port number 1, because if something leaves on port 1, that means it goes to the sink, versus something that leaves on port 2, which means it goes back to the queue. That's kind of my first hurdle. I need some piece of information on the flow item that allows me to look at the flow item and know what it did. Did it go to the sink or did it go back to the queue? So I'm going to use the events of the processor to assign a label to help me out with that. So under the trigger section of the processor, I'm going to choose the on exit event, because the on exit event fires whenever a flow item physically leaves the processor. And during the on exit event, I can know where something is going. During the on exit event, I know if it's going to port number 1 or if it's leaving on port number 2. That's just something that's built into the on exit event where I can know where it's headed. So during on exit, I'm going to add an action to this trigger by using the green plus sign and say that I want to work with some data where I will set a label. It's the first option under the data section where I want to say that a label is going to be set. So if I choose set label, then it wants me to indicate to whom we will assign this label. In this case, it's using a keyword that we'll talk more about later on called item, that allows me to indicate that the item that is exiting the processor is going to be the owner of this label. So that's what this first input field is asking us for, is who is this data going to be assigned to? So we use the item keyword to say that it's assigned to the flow item that exits the processor. And then we have the ability to assign the label a name. So notice in there that we just have a placeholder name type, which is a fairly common label name. It's used for a lot of things. You don't have to use it if you don't want to. And in fact, in this case, type might be a little bit too vague. And instead, I might call this rework state, because that's what this label is going to keep track of. It's going to keep track of the rework state of a flow item. Was it rework or was it non-rework? And so notice that the name of the label is indicated between a set of quotation marks. When we're naming a label like this, it wants the text of the label name to be between a set of quotes. So remember that this corresponds right back to what we talked about earlier with regards to the labels, where we indicate the label owner, we indicate the label name. Now, notice the way I named this label. This is the way that I tend to name my labels. I start with an uppercase letter for the label name, and then I also leave spaces out of the label name. I don't have to. I could name it like this, where it was rework state, like that, with a space between rework and state. But there are some things that actually make that difficult to work with in some later versions of the model that we're going to see. So I'm just going to go ahead and take that space out of the name because this is how I like to name my labels. It makes certain things a little bit easier. And so in addition to the owner of the label, the name of the label, now I need to indicate the value of the label. What is going to be the data that is actually being carried by this item in the label called rework state? Right now, it's going to be a random number given by the D-uniform distribution with a minimum of 1 and a maximum of 3, which isn't terribly helpful for what we're trying to do here, because what I want to know during the on-exit event is where the flow item got sent to. I want to know if it got sent to port number 1 or if it got sent to port number 2, because those two different port numbers will tell me if it's a rework part or if it's a non-rework part. If it got sent to port number 1, then that means it went to the sink. It's a good part. If it got sent to port number 2, that means it needs to be reworked. And so in the value input field, there is a pre-programmed option that lets me do that called port. So I'm going to choose port, and it's going to fill in this keyword port. So during the on-exit event, the output port used by the flow item is known, and it is referenced using this phrase, this keyword port. And so that means that if the item in question uses port number 1, then the value of port will be the number 1. If it leaves on port number 2, then the value of port will be a number 2. Everyone okay with that so far?
Yeah.
So let's just see what that looks like. So if we hit reset and run on this now, the first flow item gets processed, and right before it finishes, I'm going to stop the model. And if I click on the flow item, I want you to notice that in the properties of the flow item, there is a section dedicated to labels. And right now, there are no labels assigned. This area here is empty. You can also see that if you double click on the flow item and go to the label section, and you can also see that that area is empty. But I just like to do the single click and see it over here. And now watch what happens when the flow item gets picked up. So if I hit run again, operator picks it up and I stop the model again, click on the flow item, and now it has a rework state label that indicates the value of 2. So that means that I can know that this flow item is on its way back to the queue because its rework state is already set to 2. So let that continue, gets dropped off. Now we picked up this other flow item. If I stop the model, I can see that this flow item, this is the first time it's been through the processor because it doesn't have a rework state label on it. But then when the flow item gets picked up again, it has a rework state now of 1. So now by looking at these flow items, I can say, okay, I know where you're going. You're going to the sink, so you're a good part. And if I click on the one in the queue, its rework state is 2. I also know that means it needs to be reworked. So now the value for rework state, either 1 or 2, tells me what kind of flow item it is, what its current rework state is. This one is a rework state 1. It's on its way to the sink. This is a rework state 2, which means it's about to be reworked. Now, if we watch this run for a while more, again, keep an eye on this flow item. We can see that it's going to get reworked once. Actually, that was twice. Now it comes back again. This is its 3rd try. Rework state remains a number 2. Now for its 4th try. Rework state remains number 2. And now we're on our 5th try. And notice what happens this time when it gets picked up, where the rework state, oh, one more. We need one more round. So this time we're going to wait for it to get picked up. And now it's a rework state is now gets set to 1 because now it's leaving the processor on port number 1. So that's another key feature of labels, that even though it was assigned a value of 2 initially, we can update the value with new data as we go through the execution of this model event, these model events. So even though initially when that flow item left the processor, it was given the rework state of whatever port was, in that case it was 2, because port is either a 1 or a 2, depending on what port was used, we updated the value of rework state to a 1 when it finally left the processor on port number 1.
Is there a way to get historical label data so that we know, like, oh, it got reworked 4 times, it got assigned that label 4 times, and then it got assigned this new label on the 5th time?
Yeah, there's actually a couple ways to do that. There is a special label data type that you could assign that keeps a history of values rather than just what the most current value is. That's a little bit more complex. You could also just do what we call an increment on that label value, so that rather than being set to either a 1 or a 2, you could like count the number of times that it happened. You could keep a count of how many times it got reworked, or you could, like I said, use that other data type that keeps a record, and you could say like how many records are there in the label. So there's a few ways to do it. It just kind of depends on which way is like simpler and more direct, and which one gives you the information that you really want. Because like the nice thing about the what's called the tracked variable data type is, since it does keep a history of all the values, that might tell you something more than just like how many times, right? Because it would tell you how many times based on how many records there are, but then it could also tell you what those individual values meant. If there was like more than 2 possible values, it might be useful for something like that.
Okay.
So short answer, yes. So now that we have these labels and we can tell the difference between a part that needs to be reworked and a part that is good to go to the sink, now we can use that information as a way to enhance our outputs on our dashboard. So I'm going to click on my dashboard window to bring up my template library. And under the output section of the library, I'm going to choose the option that says that I want to look at my output by type. So output by type means that we're going to be looking at a throughput-based statistic. But because it says by type, that means that we're going to use a label value to differentiate between different kinds of output. So if you click on that output by type, it gives you 2 different ways that you can visualize this stat. You can either visualize it as a bar chart or as a simple table of values. I like the bar chart though, so I'm going to choose the bar chart option. And then I'm just going to click that chart into existence on my dashboard window. Now, notice that your cursor, when you do that, is changed. This is an object creation cursor. It's a different mode. If I were to continue clicking in the dashboard, it would continue making more and more charts of the last chart type that I just made. But to get out of this mode, just right click and you can get back to your standard cursor again, just like we did with the port connections. Now, with a chart that we get out of the template library, we have to configure the chart. And so when you click on a chart, you get the configuration options, the properties for the chart on the right-hand side, just like you do for an object. And one of the first things that it wants to get from you is what object we're going to gather data from. And you can either add objects by clicking on the green plus sign, or you can use this little sampler icon where you can sample an object and add that to one of the objects that you're going to report on. So they're essentially the same thing. They just use a slightly different interface. If you click on the green plus sign, you can say that you want to select objects and it will show you the different classes of objects that you can add to this chart. But if you use the eyedropper, then you just click on the object and it just gets added to it. So I would say if you're just adding like one or two objects, the sampler is kind of a nice way to go. If you're adding a bunch of objects, then maybe the green plus sign is nicer because you can add these objects like all at once. You can say, okay, I want the processor and the separator and the source to all be added to this chart all at the same time without having to find them and actually click on them. So, okay, now right below the object that we want to gather on, that we want to gather the data from, it wants to know the name of the label that it should look for on the flow items. And so it defaults to the label type, because whenever you set a label on something, the default label that we usually give you is type. But like I said, you can name this to be whatever you want. It just has to match what you have in your model. So since I named my label rework state spelled just like that, then I can put that in. Now, if you misspell your label name, or if you don't take into account case sensitivity, then the chart will display no data. It won't give you an error, but it just won't display any data. So be really careful here that you verify, okay, my label name here is rework state with uppercase R, uppercase S. And then on my chart, I have to say, oh, that's not spelled correctly or whatever, and make sure that those label names are an exact match. This is as good a time as any to tell you guys that everything in FlexSim is case sensitive. This is the first time that we've really seen it. So it's the first time that I'll mention it, but just keep in mind, everything in FlexSim is case sensitive. So just, pay attention to the way you name things and make sure that you're consistent. Okay, so now if I hit reset and run, I'll just speed this up a little bit. We should see that we are going to get two different bars in this chart, one that tracks the throughput of the rework parts and another one that tracks the throughput of the good parts. So we can see here that we have 2 things that were good versus now 7 things that needed rework. And so over a small sample size, that might be an unexpected result based on the 80-20 split. But now as the model continues to run, we'll start to see those bars more closely approach the percentages that we would expect. Because like all things in statistics, a small sample size may be misleading. So we have to wait for a larger sample size to make sure that the values make sense with the percentages that we assign them. So right about here, we can see that after about 100 flow items, pretty much what we would expect. 80% were good parts and 25% were rework parts. And again, it's the label that lets me do that, because otherwise I would only have the input of the sync to go by, which is 80. But now I can see that, there's my good parts of 80, and then here's my rework of 25. I had 25 rework events in my model versus 80 good part events on the processor. Okay, any questions there at all?
Yeah. How I know it says 80-25 right there on the graph, but is there a way to get the graph to also display the percentages? Or is there a way that, can you then take the 2 values in the graph and maybe sum up the difference? Or what if we took like the output of the processor and the sync, and then have those on the same graph. We change the graph to do the math for us that says, here's the difference between those two pieces.
I mean, yeah, you could. It's a little bit more work though, because what you would have to do is you'd have to create it's an object that we call a statistics collector, or stats collector for shorter, that would be monitoring the input stat of the sink and also the output stat of the processor, and then displaying a value that was a mathematical expression of those two values. But you'd have to create your own stats gatherer to do that, whereas doing the label method is a lot simpler. But you could definitely do it that other way if you wanted to, but it would just require the application of a customized stats collector, because the charts here only know how to display the data that they're designed to collect, and they use the stats gathering functionality to create basically a set of data that it can turn into a chart. And so you'd have to collect your own set of data and then create a chart that looks at that data to display the information the way that you want. I mean, you can kind of see that where in the toolbox, I have a couple of stats collectors that are gathering stats for the content versus time chart and the throughput chart. And this throughput by type chart is also using its own stats collector that's kind of hidden behind the scenes. But we use these mechanisms to gather stats based on the events of your model. And so you would have to create your own stats collection methodology so that you said, I care about these events and these stats during these events, and then I want to perform this mathematical operation on these two values during this event to display my value. So again, short answer, yes. Long answer, it takes a bit. Good. Any other questions so far? Okay, so one of the key ideas that we're also introducing at this time is this idea of data management, right? Where we have data in the model and we're looking for ways to display it, like in the case of things like throughput by type. In this next section, we're going to go over some other data management capabilities of the software, introducing them and using it to get us access to some other important information that we may need in the model building process. So that means that we're going to introduce the idea about using table structures as a way to organize important model data. And we're going to take a look at table structures in the form of a global table and also the empirical distribution table. So we'll talk about tables kind of generally, and then we'll talk specifically about how to use these two particular kinds of data structures in order to amplify your models a bit. We're going to continue using labels in this next section, again, because labels become super important for a lot of things. So we'll continue our use of labels. And we're also going to take a minute to take a closer look at what's going on during trigger events of our objects. So we've kind of just sort of skated around triggers a little bit. We haven't really gone into a lot of detail. So that's going to be one of the first things that we're going to look at in preparation for phase 3. So one thing additionally to note about label use. Now, in the last example, we used labels primarily as a way to, well, the only way that we used it, not just primarily, but the only way that we used it was to allow us to change the way stats are reported by the model. And that comes up quite a bit. But we can also use label information as part of the configuration of objects, part of the object properties, to be able to say that label data impacts choices that objects will make in the execution of their events. Like, for example, in the output section of your properties in send to port, you might say something like the port that we want to use is found by looking at the item and then using the part number label as the port number. So this is an example of this sort of expression syntax where you can access the information stored in a label where first you designate the label owner, like item, and then use the dot operation, and then the name of the label that you assign as a way to say that I want to get the value found in item dot some label name, in this case, item dot part number, where you can say that I want the data stored here and I can access it using this kind of an expression where it says item dot whatever label name you might assign. So like on our current example, if I wanted to access this information for some reason, then I could say, well, look at the item and look at the rework state label. So item.rework state, and it would report back to me the value 2, because it would tell me what information is stored in the label designated as item.rework state. And so that's kind of the same idea that we're seeing here, where we're saying, give me the information stored in item.partner. Okay. Now, this also leads me to a little bit of explanation of why earlier I recommended to leave white space out of label names. So compare these two accessing expressions. Item.labels, bracket, quote, stocking space number, close quote, close bracket, dot value. Right? It's a lot to type. If I take the space out of the name, stocking number, I can just say I can instead just say item.stocking number. So one of these is easier to type than the other. And so I would recommend not putting spaces in your label names, just so that I don't have to worry about doing this big long expression with the brackets and the quotes and everything. Instead, I can just say this short version, which is item.label name with whatever label I want. Again, staying consistent with the way that you name things.
Do labels only take alphanumeric, or could I put an underscore or hyphen if I really felt like it?
Yeah, great question. Underscore, yes. Hyphen, no. Yeah, because it would interpret the hyphen as a subtraction operation.
I'll just take alphanumeric or alpha.
But numeric is fine too, right? I mean, as long as the first character isn't a number, you could say stocking number 1 at the end of that. That'd be fine.
Okay. Okay.
Right. But you just wouldn't want to start it with 1, like the number 1, and then stocking number. And it wouldn't like that, because it would think that you're referencing a value instead of a label name. So alphanumeric is fine as long as the first character is alpha. But special characters, except for the underscore, are not allowed. Underscore is fine. Everything else might get interpreted as like a mathematical operation or something like that. Okay, so that's going to come up in some things that we're going to do later on. So just kind of introducing this idea of being able to access a label over the course of the model execution as an input to an object parameter or an object property that might be useful for some things. Now, like I said too, I wanted to spend a little bit of time going over triggers a bit, because we didn't really talk too much about what they are and like what kind of information is provided during a trigger. So it's a good idea to spend some time thinking about that. So the main thing to remember about triggers, first of all, is its definition, that a trigger event is an event that happens in response to a key event on an object. So like on the example that we had of using a trigger so far, we said that on exit, we want to do something. So the on exit event actually happens as a response to something leaving. So that's the way that pretty much all the triggers work, where the event of a flow item leaving an object happens, and then the trigger happens after that. So triggers fire as a response to important events. And during those trigger events, we can add actions. We can say that there are things that we want to have happen because that event took place. You don't have to use those trigger events if we don't want to. The trigger events are going to happen, whether we use them or not. It's just a matter of whether or not we want to piggyback any custom model behavior when that event happens. And so that's essentially what we did with the example that we saw, where the on exit event happened, and we said, when this event takes place, add this label to the flow item. And so the name of the trigger tells us when it happens in the flow of the execution of the object events. And then we can use the green plus sign to add additional actions to the trigger. So like one of the things that differentiates a trigger from a regular object property like send to port is that if I open the actions that are already on the on exit event by clicking on the edit button, notice that I have a green plus sign on this window. I can add additional actions. So I can, do all these different things to say, hey, when the on exit event happens, I want to set this label, I want to send this message, and I want to set this color. And you can add as many as many or as few of these actions to the trigger that as you want, and like I said, contrast that with like an object property like send to port, where I can't add additional actions that are separate from the send to port. I can't say send to port by percentage and also, send to a round robin port. It wouldn't let me do that because you could only have one action assigned to an object property like these. But with the trigger events, you can add multiple actions. So they're provided as a way for you to conveniently associate your custom object behavior to the event that the object is going to execute anyway. So like in our case, we said, hey, the on-exit event's a really convenient time to know whether or not something needs to be reworked or not. So we're going to use the on-exit event as our rework recording event. We're going to say that when this event happens, we know when something important is going on. So I'm going to save that information potentially as a label onto my flow item. Now, whenever we have actions that take place during these triggers, there might be objects that we need to affect as a result of those trigger events. And so there is information provided during the trigger events that allow you to target objects as like the recipients of the actions that you're going to take. And we saw that with, again, our example here that said set label. And we said the object that we want to reference, the object that is going to be assigned this label is indicated with this keyword item. But in the drop-down menu for this, you'll see that there are other ways, other objects that could be referenced. You could reference objects based on connections that they have to other objects, or by using these keywords current and item. So to kind of help us understand these different ways of referencing objects, I'm just going to open another FlexSim for a second. I just want to show you a couple things that hopefully give us a good definition of what these two important keywords are, current and item. Okay, so I'm just going to make a couple of objects. I'm just going to have a source and a queue. I'll connect the source and the queue together. And during the on-entry event, the on-entry trigger of the queue, I'm going to say that I'm going to choose an option under the visual section that says that we will set the object color. And so notice here that the object that is going to be the recipient of the color is indicated as item. And the color that we're going to assign is going to be a random color. So we define item as the flow item that triggers the event. So it's the reason why the on-entry event in this case takes place. Because the on-entry event will only happen if a flow item arrives into the queue. So if you hit reset and run, the result that we see of that trigger event is that when flow items arrive, they arrive and are assigned a random color. So again, if we take a look at the properties of the queue, find the trigger section, and open the action that we have there, it says that items will be assigned a random color. And it will only happen during the on-entry event. Right? If I take this action out, if I reset my model and remove this from the trigger and hit reset and run, then the flow items all come in as a brown box. But if I go back to my on-entry trigger and say that I want to choose a visual option, and we will say set object color, then now the items are assigned a random color. So now when they arrive, they're just assigned some random color. So far, so good?
I don't understand the slide that you showed. So the slide shows it circles current versus item.
Mm-hmm.
So if you select, so you have item selected now, right?
Correct.
What if you select current?
Great question. So let's start by defining what current means, right? Current is the owner of the event. So if we're looking at the on entry trigger, current is the object that owns on entry. So if I come back to the queue, and instead of saying that the item is the target object of this set color, and instead say that it is current. Now who's going to be assigned a random color?
The queue?
Yeah, because the queue owns the on entry event, right? So if we hit reset and run now, then during the on entry event, the queue has its color changed because now we've indicated that the current object or the owner of the event is going to be assigned a random color. So the boxes retain their original color, but their arrival triggers the color change on the queue.
Okay, yeah, I didn't realize changing the color of queue was an option.
Yeah, you can change the color of anything.
Got it.
But this is a good way to kind of differentiate between item versus current, right? Because again, these are different objects that have access to different kinds of data. There might be things about the queue that we need to be able to get access. There might be things about the flow items we need to be able to access. And so current and item give us a way to do that. You can kind of consider them like pronouns. They're ways of referring to objects without having to know the specific object. We know that current owns the events, and we know that items are the cause of those events. Okay, everyone okay with that so far?
I have more of a generic question. Because every object we can change a lot of things. Is there like a one-stop place where we can see what are all our settings that we have kept for all of the objects?
Aside from the object properties, not really. Okay. Yeah, the object properties is kind of the mechanism where you can see where all those are, if I'm understanding right.
Okay, so nothing like a debug panel or something where we know what everything is set to, so that we can debug easily.
Yeah, not really. In individual events, there are debug options associated with like the code behind the scenes, because like all of these actions that we choose, like whether it be like send to port or on entry, there's like modeling code that's behind the scenes. Mm-hmm. And you can debug that with like some special tools. But aside from that, yeah, not really, I don't think.
Good.
Okay, so main thing there is just, again, kind of taking away this idea of current versus item as a way to access information associated with either the owner of an event, like current, like the queue, or item, like the flow items that are causing the event to actually happen. Okay, and again, keep in mind too that this is the reason why flow items tend to represent that central actor concept that we talked about earlier today, where the presence of the item is causing the queue to react to its presence by, in this case, changing its color, or like if it goes to a processor, it does processing time. So the flow items are causing objects to react to their presence by executing events. Okay, now in addition to being able to reference objects like current and item, there are some additional expressions that might be useful to be able to reference other objects in the model by leveraging their relationships with other objects. Or said in other words, being able to reference objects that are connected via port connections. And so we use a similar syntax pattern as what we saw with the label accessing, where we say label owner.label name. You can also access objects that are related to other objects through port connections by first referencing the object, then using the dot operation, and then defining the connection type. And then inside of a set of brackets, indicating the specific port connection number that you want to reference. So the way that this is most commonly used, where we see this all the time, is in places like use transport, where we said that we want to reference the transporter as being an object that is connected to current on a center port connection. And then inside of the brackets, we reference the number of that particular connection. So this would be a way of saying, I want my transporter to be the first of the center connected objects associated with current. So that's why things like this work, where we say that the transporter is operator 1, because operator 1 is connected to the queue on its first center port connection. So like, for example, if I had that same little example model, and let's say that I had an operator out here, and I connected the operator to the queue on a center port connection. And now if I go back to that on entry trigger and said, instead of current or item being the object whose color gets changed, I can say that instead it is one of my connected objects referenced as current.centerObjects bracket 1. So now if I run the model, instead of the boxes changing color or the queues changing color, my operator is going to change its shirt color. Because again, the object that's referenced as the target of this random color is connected to current on a center port, and then we use the number 1 to reference that particular connection on center port number 1. All right, any questions there so far?
I have a quick question. Is it possible to reference events or triggers of the whole model, like on model end? Like I noticed whenever you press reset, your queue didn't default back to the normal color.
Right. Yeah, so that's actually a really good question. Not only do individual objects have trigger events, like what we're seeing here, but also if you go under the toolbox, there are, let's see, it's under modeling logic. There are entire model triggers as well. Like there's a trigger for when a model gets opened, when a model gets reset, when a model run starts and also stops. So these are trigger events that belong to the model as a whole, as opposed to individual triggers that belong to individual objects. Right. And so like, as far as like how the queue remains this kind of rusted color, even though I hit reset, it doesn't know that it's supposed to default back to gray. But I could say that during the queue's on reset event, because there is a trigger for on reset on the individual object as well, I could say on reset, set the object color, and instead of, well, I'd have to say current, so that it gets set to the current object. And then instead of a random color, I could say it's going to be gray. And then when I hit reset, it goes back to being a gray queue instead of the multicolored queue that I made it earlier. So yeah, you can either do stuff like that, you know, on the individual object itself. There are also the model-wide triggers available here, where you can say that there are events associated with these events of a model as a whole, or the events associated with individual objects. Now, I'm illustrating this idea with changing of colors just because it's a really nice visual way to illustrate this. But if you can access an object through things like item or current, or through the port connections like center objects, out objects, and in objects, that gives you access to whatever data you need on any of those objects. So if you needed to access the labels of an operator, then you could use current.centerObjects1 to get you first access to the object, and then use the dot operation to get to those object labels. Right? It just allows you to establish whose data you're interested in accessing. And the color change stuff is, you know, a nice visual way to illustrate that idea, but it goes way beyond that if you needed to. Hey, any questions at all? Okay, so in this next section, kind of the big new idea for this phase that we want to talk about is the use of tables. Again, I kind of mentioned that we're working with tables as a way to manage data, kind of similarly to the way that we use labels to manage data. But the big difference between tables and labels is that typically a label is for managing a single value or a set of values that are associated with a particular object, like a flow item or a processor or something like that. But with tables, typically the information that we store in tables are more something that needs to be accessible to the model as a whole. It's more like model-wide data as opposed to just a singular value that belongs, like an attribute to like weight to a single object. And so we have these different table structures in FlexSim that behave like spreadsheets so that you can easily bring in external data into FlexSim for use if you need to, or to build a table of data as your model runs in FlexSim. A lot of different ways that you might manage it. And so to kind of give us some different options, we've created a number of different table structures in the software that allow us to organize model data in some fairly easy ways. The first two table the first two table structures that we're going to be looking at in this phase are the use of global tables and empirical distribution tables. And tomorrow, these other two table structures that we're going to talk about, parameter and performance measure tables, we'll talk about those at some point tomorrow, kind of like midday-ish or something like that. But introducing the table structures, first of all, that we'll want to take a look at is this idea of a global table. Now, in the different table structures that we have different kinds of data that can be assigned to the actual cells of the table. Some of those data types are very simple. Some of them can be a little bit more complex, like the simple data types that we typically work with are numbers, that represent different values, different numeric values of your that are important to your model, or strings, which would be just like strings of text, like names, words, sentences, things along those lines. And then some of our more advanced data types can be used to really enhance the information stored in your table, like having what we call a pointer or a reference to an object in your model, arrays of data, actual FlexScript, which is our coding language for managing simulation models. You could have FlexScript data stored in your table. And really, it opens up a lot of different things that you could potentially do. But in this section, we're mostly going to be concerned with just the simple data types to kind of get our feet wet with the use of tables. So by default, when you create a global table, the data types for the cells are assumed to be numeric. But if you wanted to change any of the data stored in individual cells or rows or columns, you could select them on the table interface, right click, and that would give you this interface where you can assign any of the other data types to either, like I said, a particular cell, row, or column of the table. So let's talk a little bit about global tables first of all. Global tables are pretty open-ended. They are the most like Excel in the way that we use them, because the data stored in the table is assumed to be whatever you want it to be. There are like no default actions associated with a global table. It's something that you can add to your model, and then it's up to you to decide what kind of data is going to be stored there, how that data is going to be formatted, and how your model is going to access or manipulate the information that it finds there. By default, when you create a global table, by going to the toolbox area of the library and going to the global table option under the green plus sign, that global table by default is just a single row, single column table. And then it's up to you to enhance the way it's handled by going to the properties panel for the table and indicating how many rows, how many columns. You'll notice that it has its own reset trigger. So if there's something you want to happen to the table on reset, you can define that. Also notice the Excel button, which means that you can easily import and export data with Excel and the global table if you want to. Okay, so like I said, the information stored here is entirely up to you. Whatever it means, however it's to be used is entirely in your hands. Once you add that information in the table, though, you'll find that there are options associated with things like object properties that would allow you to use a table as like an input to an object property. Like, for example, you could use a by global table lookup option associated with an object property like maybe processing time, and say that rather than using a distribution or a value directly into that object property, maybe that value needs to be found by looking it up from a table called processing times. And then you use a label value potentially to tell you a row of the table and a column where you want to read a particular value out of the cell of that table. So rather than using the distribution or some other value, you could say that value comes from a global table instead. So there's a lot of options built into the object properties where you could say that you want to do things by global table lookup. And then you just have to provide the table that you want to read from, the row value that you want to read from, and the column value that you want to read from. Now, in the event that one of the inputs that you want to use doesn't provide a by global table lookup option, so you have this nice interface for choosing the table name, the row, the column. You could also access table data using this kind of an expression, where you would say capital T table, and then inside of parentheses, you have the name of the global table that you want to access, contained by a set of quotes. And then you have in the bracketed values a row number or expression, and then a column number or expression that would allow you to access the value stored in that cell given by the row column coordinate. Any questions on that so far? Okay, so really think of a global table as really like having a completely open-ended spreadsheet style table that you can embed directly into your model. Now, the global table doesn't assume anything about the way its data is going to be used or how it's going to be accessed. Some of our other table structures have very specific uses, and so they have a little bit more rules about how they're going to be used. And so an example of that would be the empirical distribution table. The empirical distribution table is useful for bringing in time study data directly into a model and using the information there as a customized distribution. So rather than using distributions like exponential or log normal or something like that, you could use the empirical distribution that's made up of your own custom data directly without having to figure out, does this data look like a log normal distribution, or does it look like, a Weibull distribution or something like that. So to create an empirical distribution, again, you go to the toolbox, and under the statistics submenu, there is the option to add an empirical distribution table. And the empirical distribution table, since it has a very specific use, it has certain rules about how you can set it up. You can still have as many rows as you want, but in the continuous mode, it only lets you have one column of data. And essentially what that one column of data represents are the data points that you want to be valid in your customized distribution. So essentially what it does is it takes a set of data that looks like maybe like this, where you have like 42.84, 112.62, 78.51, and it allows you to graph it so you can see the frequency histograms associated with those data points. And then you can use the information that it finds here as inputs to object parameters like processing times or the way labels are assigned or something along those lines. So like, for example, if I were to come over to our model, actually, I'll do this in this other little example model here, and we'll just kind of add in some more stuff. And I happen to have an Excel sheet that has an example of what the data for an empirical distribution might look like. So you can see it's just a single column with a bunch of random numbers in it. And I have 200 data points. And I want to use this data as maybe the processing time for my processor. So rather than like trying to choose a distribution from the drop-down menu here, where I say, well, I want to use like one of these, maybe I know what my distribution values are, but I don't know what curve they correspond to. I can use them directly by going to the toolbox and saying that I want to create an empirical distribution. And I'll say that we have 200 rows. And then on my Excel spreadsheet, I am going to copy. And then I will come over to FlexSim and paste. And if I click on the Generate Samples button, it shows me this is what my distribution curve looks like for this set of data. The blue bars represent the values from my data file, and the green bars represent the fitted values, where I can get values that aren't necessarily in the data set, but they're extrapolated to be part of the data set according to the fitting algorithm that we use for the distribution. So now if I want to use this continuous data set as a processing time, I can do that. And instead of like, I'll call this processor time data. That's the name of my distribution now. And then if I come over to my processor, instead of using, one of these distributions, I can come down to the bottom of this list and say, I want to use an empirical. And I can choose from the drop-down list that it knows that I have a distribution called my processor time data. And now when I process things on that processor, it uses the distribution data from this data set as opposed to its own data file. And I can see that on the state time that we have a min, max, and average value that falls pretty much what you would see on this data set. And again, remember that the blue bars represent the values from the data set directly. And then the green bars are the continuous sample values that are generated from that data file. So essentially what it does is it extrapolates green bar values that fit into the curve defined by the blue bar values.
Why would you want to extrapolate those values? Like, why wouldn't you just use what you already have?
Yeah, good question. So because this set of data might represent 200 observations from the real world about how long this process takes, but maybe values that aren't explicitly in the data set are still potentially valid, but they just don't occur in the data set. Right? And so the green bars allows values that don't appear in the data set to be extrapolated from the values that we get in the blue bar set.
Yeah, okay.
You know what I mean? And so if you were to switch the distribution type over to the discrete mode, then the values that you get out of the curve are only values that appear in the data set. Those become the only valid values. And so there are reasons why you might choose it either way, right? Because if the values in the data set truly represent all of the possible values that you could have, then discrete makes sense. But if the values in the data set just represent a sampling of potential values, then continuous probably makes more sense.
Okay.
Now, the discrete versus continuous, like I said, is kind of setting up a way that you can kind of figure out what are the valid values that you could get out of this distribution. Continuous is probably the most straightforward because it just says, okay, we're going to figure out, based on your data set, all the potential values and their distributions based on the data set that you provide. You don't really have to do very much here. You can just provide this data set and it's fine, right? Now, the discrete distribution, like I said, it also now limits you to only being able to have the values that are in this data set. Now, sometimes that can be really useful. So to kind of illustrate this, I'm going to create a second empirical distribution that is going to be set up as discrete. So I'm going to go to statistics, go to my empirical distribution. And here I'm going to say that this is a discrete distribution. And rather than having a data set, I can just say, well, let's say that we have 4 possible values. And so the data, when you're using discrete, it could be either number or string. When you're using continuous, it has to be numeric. But for data, I could say that this is, type 1. Oh, wait, I forgot. I got to set the data type to string here. And I can say this is type 1. This is type 2. whoops, type 3, and type 4. And so these are the potential values. And if I generate the samples, you'll see that those values occur roughly evenly because there are 4 values and it just naturally splits them into even distributions, right? Because type 1 occurs once in the data set, type 2 occurs once in the data set, and so on. So if I added like a 5th one and said, okay, this is also type 2, then that's going to affect the sampling because now type 2 has a greater chance of occurring because it occurs more often in the data set. But another cool thing that we can do with things like discrete is that if I don't want to have to put in the values in order to establish the histogram for the for those values, instead I can apply a weight to those distributions. And so this, again, this is something that you can only do with the discrete distribution, where I can say that there is now a weighting column. And so under the weight value, I can establish a value that represents how frequently this value should occur. So like if I say that, you know, it's 40 for a weight of 40 for type 1, a weight of 20 for type 2, a weight of 50 for type 3, and a weight of 70 for type 4, then when I generate my samples, it builds a histogram bar out of that. So it says, okay, well, based on the weights that you put in there, 40, 20, 50, 70, that means that type 1 would occur 22% of the time. Type 2 would be 11.53% of the time, and then 27.31 and 38.48. So these weight values are establishing the heaviness or the frequency with which these values in the data set could occur. So if you wanted to, you could think of these weight values as like a percentage. So, I mean, like right now, you notice that these don't like add up to 100% at all. And I did that on purpose just so you could see that you didn't have to have a weight value that was up to 100%. But if you wanted to, you could say, okay, this is 20, this is 20, this is 20, and this is 40. Right? And then when you generate the samples, you can see that it kind of gets really close to those percentages that you added. So 20.11, 20.15, 19.75, 39.98. And again, like I said, the data here, it could be a numeric value or it could be text. But again, that's only in discrete mode. And so why would you want to do that? Well, what if these values represented labels that needed to be assigned? You could do something like this over on the source, where you could say on exit, I want to set a label, whoops, data, set label. And that label name, we'll just leave it on type. And then for the value, now this is something that was recently added. This was in 21.13, you should have this option in the pop-up menu that says empirical, and then you can choose the name of an empirical distribution directly from here. If you don't see the uppercase E empirical, then you will have to type out this expression as it appears on this slide, where it says empirical and then the name of your distribution .get. And then this get stream current part is optional. You don't have to put that part in if you don't want to. But you would need uppercase E empirical, parentheses, quotes, name of your distribution, close quote, close parentheses, .get. And that would allow you to sample a value from that distribution. And so what I did here, it just automatically filled it in for me because in 21.13, we put this into the set of options from this pop-up menu, but it wasn't there before that. So if I leave it the way it is, notice it has the name of my distribution here, name of distribution here. And so when a flow item leaves the source, take a look at this box, it now has a label called type, and the value is type 1, which comes out of the empirical distribution table. And again, if you switch this from string to number, if I say that the values are 1, 2, 3, 4, and do this again. Now, instead of saying that the type is the text type 1, now it's the value 1 as it comes out of the data column. And so here I used the empirical distribution as a way to randomly assign label data according to some pattern that I wanted to use to assign it. And that's a fairly common thing. I think these empirical distribution options are relatively new. They were first put out at the beginning of the year for version 21. And I think these are going to be a really useful tool going forward because, you know, a very common question people asked was to say, well, how do I get my real world data into the model? And it was kind of a roundabout process before where you had to take that data and do a curve fit on it so that you can see, well, your data kind of looks like the log normal distribution or something like that. But now you can just use these empirical distributions directly. And you can even use the discrete empirical distribution to construct a custom distribution with values and weight values that you want to define those values frequency. So it's kind of a neat tool. I think a lot of people are going to like this going forward. It'll make certain aspects of your model easier to do than they were in the past. Okay, any questions at all so far?
From your experience, Regan, what are some of the most common actual applications where you and other customers are using the empirical tables?
Yeah, so there's probably like 2 ways that I've seen, because we've had empirical tables before, but they were harder to use than they are now. And the empirical tables were really useful for like taking time study data. That was like the way that I saw it most. Like they have like a database of values for like how long it took for a particular process to execute, right? And so you're getting this data dump from the machine itself that says, when I worked on this part, it took me this long. When I worked on the second part, it took me this long. So it was this big table of data that basically outlined, these are all the processes I did today, and this is how long they took. And like I said, historically, to get that kind of data into a model was kind of a multi-step roundabout kind of a process. It was a little bit of a pain in the neck because you had to take that data and run it through a separate piece of software that knew how to do a curve fit. And then it would say, well, your data kind of looks like this curve. And so you could use this curve with these parameters at like the processor that represents that process in your model, and it'll probably work. But a lot of times too, when you did those kind of curve fits, you would find that your real world data didn't really look like a curve, or it was like a bad match for a curve. And so it kind of wasn't like a great way to get your real world data into a model. And so the empirical distributions were nice because you could just say, well, take the data however it is and just use it as is. And you don't have to worry about it not looking like a log normal curve or not looking like a Johnson curve or whatever. You just use the empirical distribution to say, this is the data, this is what it's going to look like, and just go from there. The other way that it gets used a lot is for like assigning attribute data, where you have like certain kind of data, like maybe the weight of a thing or a serial number of a thing, a skew of a thing, and they happen randomly, but again, in a way that doesn't really fit to a curve very well, especially if like the values that you want to assign are text representations as opposed to numeric value representations, because you can't make a distribution curve like log normal that uses text values as the outputs. It can only return numeric values. And so using the discrete empirical distribution is nice because you can output either numeric values or text strings, you know, like what we did when I switched the data type over to string and said, you know, it's, you know, type 1, or this is Bob, or this is XYZ 1, 2, 3, something like that, right? The distribution curves don't do this very well at all. But a discrete empirical distribution can handle this pretty nicely. Then you just have to use the weight value to determine how frequently these values will occur. So it's really about having more control over things, I would say.
Yeah, that makes sense. That helps. Thanks.
Okay, so I want to give you guys a chance to practice using some of this. So I've got a little example model that doesn't change the model itself very much. Like you're going to have all the same objects and everything. And so this phase is really about data management. And so this part is a little bit difficult. And depending on how quickly you guys get through this, this may end up being the last thing that we do today. It's close though. We're right on the line of being able to do phase 4 today as well as phase 3, but a lot of times we end up finishing on phase 3. So just kind of putting it out there that this might be the last thing that we do, depending on how well we understand this. And so the main thing that we're going to be getting here is managing the information that enhances our model a little bit. So the first new thing that we want to add is that we want to add a part number label to the flow items that are created by the separator. So remember that the separator receives a flow item, and then additional flow items come out of the separator. And we want to say that there are 4 possible part numbers that could occur out of a given shipment of parts. And just for simplicity, we're going to use simple numeric values as the identifiers for these different part numbers. So the data given by this empirical distribution is going to be 1, 2, 3, and 4. But we want those values to be assigned as a label to our flow items during the on-exit event of the separator, such that the value for the part number 1 will occur 28% of the time, such that part number 2 will occur 13% of the time. And so the weight column of your empirical distribution will be this second column of this example table. So you'll have one column that indicates the values that can be returned by the distribution, 1, 2, 3, 4, and then the weight column will tell us how frequently those values will occur. And so again, you'll want to create an empirical distribution table. You'll want to make it a discrete weighted distribution table. And then you'll set your data column to 1, 2, 3, 4, and your weight column to 28, 13, 32, 27. And then we want to use this data during the on-exit event of the separator to assign a part number label to the flow items as they leave the separator. That's going to be the first part of this. The second part of this is to use a global table where parameters related to the processing time of those flow items is going to be stored. So that means that the flow items, when they reach the processor, depending on what their part number is, they will use a different set of parameters for the processing distribution. So right now, everything that gets processed are all processing according to the log normal mean standard deviation distribution with a mean of 10 and a standard deviation of 3. But what we want to do instead is to say that the mean parameter will change based on what your part number label is. So if your part number is a 1, for example, that means that your standard deviation should be an 8 and your mean should be a 1. If your part number is a 2, your mean should be a 13 and your standard deviation should be a 2.5. So the thing that we're getting from this is, again, a lot of data management, where there are going to be different input parameters on the objects depending on things like the part number label that we want to assign. And that might even impact input parameters to things like distributions as well as other objects. And so I would say this is a thing that is fairly common. So it's a good thing to kind of be aware of, that you can do stuff like this. And we're going to use the table data to help us manage and organize this a little bit better, so that when we make these changes, it's just referencing the information stored in the table rather than having to store the information on the object itself. Does that make sense?
Yeah.
So my recommendation would be to start by creating the tables, first of all. So you're going to have a discrete empirical distribution for the first table here, and then you'll have a global table for the second table. And then use, again, the on exit event of the separator to access the empirical distribution to get those label values set. And then use the options on the processor that instead of having a number 10 put in here for the mean, look in this drop-down menu for an option that will let you get a value from a global table, so that you can have a value from the global table be input into the mean and the standard deviation rather than these hard-coded values. Okay, so like I said, this part can feel a little bit difficult because it's about managing the object properties with relation to the data tables that we're going to create. So I want to give you guys a good amount of time to give this a try. But if you guys get stuck, definitely let me know. And if we need to, we'll just proceed to the walkthrough from there, because I know this part can be a little bit weird. And until you get used to this kind of data organization and structure, it can be kind of tough to work with. So I want to give you guys about 15, 20 minutes to give this a try, get as far as you can. And if we need to do the walkthrough at that point, then we'll do that. And we'll kind of talk about it and why you would do things a certain way as we kind of go through it. Sound good?
Yep.
Yep.
All right, just check in with me if you need any help, and plan on doing the walkthrough in probably about 20 minutes. Otherwise, good luck. So in doing the walkthrough for this, I want to start with creating the tables. So the first table that we're going to make is the empirical distribution table. So I find that under the toolbox, under the green plus sign, under the statistics menu, and I can say empirical distribution. And I'm going to rename this table. I'm going to call this my part data distribution. And so there are 4 possible values, so 4 rows. And the distribution type is a discrete distribution, and I need it to be weighted. And so for my data, I'm going to use the values 1, 2, 3, and 4. So remember that the data column represents the values that can actually be generated by the distribution. So if I were to put in like 7, 8, 9, and 10, right, those become the values that I can get out of the distribution. They can really be whatever you want. That's the nice thing about the discrete distribution table, is that it really can be whatever values you may need them to be. But just to keep things simple, and also thinking ahead to some things that we're going to do tomorrow, I'm going to keep it so that we get the values 1, 2, 3, 4. And then for the weighting, I'm just going to put in the frequency that these values occur. So 28% chance to get a value of 1, 13% chance to get a value of 2, 32% chance to get a value of 3, and 27% chance to get a value of 4. Okay, and then if you click on generate samples just to see like what that looks like, see that the value number 1 has got about a 27.8% chance, value 2 about 12.86, value 3 32.05, 27.28. Pretty much what we would expect with a random sampling of these values from the distribution. So got my table set up. I'm going to set that aside, and I'm also going to set up my global table. And in my global table, I'm just going to put it over here on my dashboard window, just so it's not like big and in the way of my model. Now with the global table, remember that this is a little bit more open-ended. Again, I can name it whatever I want. So I'm going to call this my processing data. And we're going to have 4 rows and 2 columns. And if I want to, I can rename these columns because, again, the global table is a little bit more open-ended. I can do more things with it. So I'm going to say that this is my mean. The values in that column will represent my mean of a processing distribution and standard deviation for my other column. And again, that part isn't required, but it might be useful just to make the table easier to read. And then for the values in this table, we're going to say that row 1 has a mean of 8, row 2 has a mean of 13, mean of 5, and mean of 10. And then standard deviation of 1, 2.5, 4, and 2. And in both these cases, with the empirical distribution table, the global table, this is just information in a table, right? It's not actually being used for anything yet. So now in the execution of my model logic, I need to choose places where these tables are actually going to be enforced. So the first place that I'm going to do that is to determine the part numbers of the flow items that come out of my separator. So I'm going to go to my separator, go to the trigger options, and I'm going to say on exit, we will go to the data section and say set label. And actually in this case, I'm going to say that I want to set label and color. And obviously I haven't told you guys how to use this yet, but that's why I included it as part of the walkthrough. This is an option that I use quite a bit to automatically assign a color to the flow items or whatever object, to automatically assign a color in conjunction with the label value. That way I can visually recognize any object with a particular label value assigned to it just by identifying its color. And so what this option does is it assigns a color automatically based on the value of the label using a default color sequence that FlexSim just uses behind the scenes. And it's just useful, again, to visually validate that, if you've got like a green box or a blue box or something like that, you can say, oh, I know what label value that must have because all the blue boxes have the same label value, all the green boxes have the same label value. So here where it says set label, I need to assign my label a name. So here I'm going to call this part number. Whoops. And then in the value field, if you're in the latest version of FlexSim, if you're in version 21.13 or later from now on, if you go to the value dropdown and go to the statistical distributions options, there's going to be an option in here that allows you to use the new empirical distribution table where it says empirical, then your distribution name, and then .get and all that fun stuff. If you're using a version prior to the most recent, then instead what you're going to see in here are some commands that start with lowercase letters like D empirical, C empirical, lowercase e empirical, and all of those options use the old way of doing empirical distributions rather than this new way. I don't know why it took them so long to get the new way of doing empirical distributions into this menu. But if you download the latest version, then you're going to see it there. But if you don't see it there, then you're going to have to type this expression essentially in order to be able to sample a value from our distribution. Now I'm lucky, I can just say, yeah, I want to use that. And then in this expression that it puts in for me, I just need to substitute the name of my distribution, which I named part data, whoops, 1A, part data. I'm having a hard time here. Part data, really hard time. Data distribution. Again, keeping in mind that everything in FlexSim is case sensitive, everything is, spelling sensitive. So I need to make sure that the name that I put in here is an exact match for the name that I have over here in the table. So if I test this to see what I've got, when I hit reset and run, when I get that first shipment to come in, which is going to happen, it takes a while. You can see here now I've got 2 boxes with different colors. So if you click on the blue box that my operator's picked up, it says that this is part number 3. And if I click on the green box, then I can see that's part number 2. And again, the colors were automatically set because the option that I chose on the separator says that we will assign a label value and a color, and the color is automatically assigned based on what the value is. So if your value is a 2, that means you're going to get colored green. If your value is a 3, that means you're going to get colored blue. If your value is a 1, that means that you're going to be a red box. And if your value is a 4, you're going to be a yellow box. So if we let this just run for a little bit and get to our next shipment. So here we had 6 boxes, and looks like we've got one of each. We've got a red for part number 1. We've got a green for part number 2, a blue for part number 3, and yellow for part number 4. And again, those colors are just automatically set based on that default color sequence that we just use behind the scenes. So it takes the value, it samples the value from the distribution, and automatically assigns a color to go with it. And so now when I'm looking at my model, I can tell what part numbers I have just by seeing what colors the flow items are. And that's a useful trick that gets used in almost every model that I ever make, because there's almost always some like categorical value that indicates a different kind of thing that I want to be able to more easily visually verify by just looking at the color of something. So rather than having to like click on the box and see what number it is, I can just say, oh, okay, if it's green, I know that means that it's part number 2, because the part number label is the label that's being set and used to indicate the color during the on-exit event of the separator. Okay, everyone okay with that part so far?
Yep.
Yeah.
Okay. Now, hopefully that part didn't feel too tricky. That's probably the most direct part of this, especially if you're using the latest version. It was a lot easier than it was, like a month ago. But even just remembering you have to put in this expression isn't too bad. But this next part is a little bit trickier, because now we want to use the processing time of this processor. We want to use these 2 values as values from this table in my processing data table, where instead of using a mean of 10 and a standard deviation of 3 for every flow item, I want to say that the mean and the standard deviation varies according to the part number of the flow item. And in fact, again, just to kind of make this a little bit easier to read, you might do something like this. Say this is part number 1. Right, and then just kind of try to make this as readable as possible, where you say, okay, here's the row for the part number 1 processing times, part number 2 processing time, part number 3, part number 4. And so if you have the global table created already, excuse me, it tries to help you a little bit by going to the distribution. And if you go to the drop-down menu associated with the mean value, it says, hey, do you want to use a global table for this? And what it does is it puts in a part of the expression that we need. It says that we can use the table called processing data, which is this table. And by putting inside the brackets the number 1, this means that we will always use the value found in row 1, column 1 as the mean. So that means that if I just leave it the way it is right now, right, everything is going to have a mean of 8, because we're reading from row 1, column 1, which would be the value 8. So the number 8 would be grabbed from the table, and that would be treated as the mean to this distribution. But really what I want to have happen is, yeah, I always want to read from column 1, which is the second bracketed value. So that part's fine. But the row that I choose from should be the same as the part number as the flow item. So if the flow item is part number 1, only then do I want to read from row 1. If the part number is 2, only then do I want to read from row 2. So I'm going to use that label accessing expression that we talked about earlier to say, look at the item, and then look at the label called part number. And that will tell us what row of this processing data table to look at. So whatever the part number is, that also becomes the row reference for my global table. And that's part of the reason why I set up the tables the way that I did with part number 1, 2, 3, 4, because I knew I was going to use those values to reference the table of the global table to go 1, 2, 3, 4 over here as well. Just made it a little bit easier that way. And so I want to do the same thing for the standard deviation. So in this case, I'm going to copy this and paste it. But instead of reading from column 1 again, I want to read from column 2. Now, one of the nice things about working with the global tables is not only can you reference the rows and the columns by their numbers, like their index numbers, but you can also reference them using their names. So instead of saying, like, for example, column 1 here on the mean, I could have said in quotes, mean, and it would have searched my table and found a column that was named mean. I could do the same thing here where it says standard deviation. That would be fine as well. The name of a column, just or even the name of a row, if you had a way to get a way to reference the name of a row header, you could do that as well. But this might be nicer just for readability because it kind of says, okay, we're reading from the table called processing data. The row is found by looking at the part number label, and then we want to look at the column named mean.
If you don't put that R in standard deviation, what's going to happen?
It's not going to work. So again, spelling and case sensitivity, very important. Thanks for pointing that out. Yeah,
I saw the bracket was red for a second. Is that kind of indicator that your syntax is broken, or is that something else?
No, if the bracket goes red, that like it's just like if I click out here, you can see how it goes red around that one and that one.
Yeah.
That's telling you that those two brackets match. Because when you have things like brackets and parentheses, you have to have the same opening and closing matching things. And so it's saying these guys match together. So that's a good set. Yeah. If I had misspelled that and not had the R in standard deviation, it would have given me a standard deviation of 0. Because it would have said, hey, I can't find that column. So I guess I'll just read from column 0. And it would have given me some really strange results. So, and that's maybe one reason not to use the names of headers like that, just because they're really easy to misspell, or at least to make your headers like super simple, so that you're less likely to make a spelling mistake, like I am. But yeah, you just have to make sure that stuff matches, just like that. And so if we run this now, it's really easy to tell that the empirical distribution is working because we can see the different colored boxes that represent the different types of things. The processing time is maybe a little bit more difficult to verify because the processing mean and standard deviation, it's tough to visually see if that's working the way that we want. But this is again where dashboards can be useful, where we could potentially create a dashboard that shows me the processing statistics for each of my different part numbers. Like, see, there was a blue one that processed really fast, a green one that processed a little bit slower. But is that within like what we would expect based on the distribution that we have? Is that like within like a reasonable bounds? So to kind of visually see that, I'm going to go to my dashboard library again. And I'm going to choose a statistic that is in terms of the stay time, because the stay time tells me how long flow items spend within a particular range of model events. So if I choose stay time by type, for example, I'm going to choose the table view option. And here I'm going to say that the entrance event for this stay time statistic is the processor, the on entry to the processor. And then the exit event is also the processor. So this allows me to get the time spent just in the processor. And I want to separate my my statistics according to the part number label. And so if I run it now, I'll just run it really fast so we get a lot of data through here. So now we have a row for each of our part numbers. And now we can see the average stay time, the average processing time for each of our 4 types, and also the min and the max. And so this is giving me a feel for the range of possible values that I could get using these different means and standard deviations. So for example, type 3 has the most range, has a minimum of about 7 and a maximum of about 30, but the average isn't too far off from the others, but it has the greatest amount of variability. So we could see a very volatile processing time for the blue boxes, for example, whereas the red boxes have a much tighter range from 12.65 to about 20 with an average of 14. And so this is showing me a much better representation of how the different means and standard deviations affect the processing times for my 3 different part numbers, or 4 different part numbers. Excuse me.
Can you show one more time how you created that state time by type? I only have one monitor, so I missed it.
Sure. Yeah, so in the dashboard library, I clicked on state time by type, and then I chose the table visualization. So you can choose any of these different visualizations. The histogram one actually looks pretty cool as well, if you want to give that one a look. But I did this one as the table. And then in the configuration options for the chart, I had to choose an entrance object and an exit object. And the time spent between the entrance into this object and the exit from that object defines the stay time period. So I chose processor 1 because I wanted to get the time spent only in those 2 objects. So from the time you enter processor 1 to the time you exit processor 1, that's the stay time stat that I want. And then I said that the label that differentiates the different stay times is the part number label. So it says type in there by default, but I changed it to part number. And then when the model runs, it displays this information for me.
Cool, thanks.
So as you can see, we've got a lot of work to do on this model. We've got quite a lot of things in the queue waiting on the operator. You know, with our failure rate, what it is, with our processing times, what they are, we end up with a lot of work on hand for the operator to do. Okay, any questions at all on the model so far? Okay, then we are done right on time, right at 4 o'clock. So thanks for hanging in there today, guys. We'll just see you back here tomorrow morning.
Appreciate it. See you tomorrow.
Yeah, thank you. Would you be sending the recordings out?
Yes, I'll be sending a link to the recordings after I get it uploaded to my cloud drive.
Okay, awesome. Thank you.
Mm-hmm.
Thanks.
Thank you.
I don't want to hold anybody else, but for some reason my queue is not stacking to the sky like yours is, and I kind of want to figure out why.
I can take a look at it if you want to share your screen.
Oh, sure. So.
Well, we've got some errors here from reading an invalid row from the processing data. And so it's probably making our process times faster than they are supposed to be. So instead of doing from there, click on the edit button next to the drop-down menu. So, okay, so that looks like it should be correct. But let's take a look. Yeah, let's take a look at the table. Okay, that all looks fine. One is not a valid row name. Valid row name. Okay, so let's go over to your empirical distribution table. Okay, so set your data type to number instead of string.
Yeah, I thought I couldn't have the decimals.
Nah, that's fine. Yeah.
Okay.
Yeah. So basically, what was happening there is it was trying to interpret the text number 1 as a row header name, and since it didn't match, it said, I don't know what to do with that. And so now, if you let this run for a while, you might see a little bit more build up. So things are just processing at like 0 time; they're just done immediately.
Okay. All right. Cool. Thanks for the
looking good there.
Time there.
Yep. No problem.
All right. Thanks. See you tomorrow.
Yep. See ya.
All right.